Like, so I think we're up to, we got about 42 now. So what I'm going to do is, so as Devin said, we're going to split this up. We got a 4-hour time slot. I'm going to speak for about 2 hours. Then I'm going to hand the baton over to Devin. I'll be talking about MRG Solve, and we're kind of doing this in a PBPK modeling and simulation context. So I'm going to do just a real couple slides just to tell you where we're going today. I'll be talking about simulation and some optimization, and it's really about optimization. And so we're going to take this model and do that for a couple hours. We'll break. We'll hand it off to Devin, and Devin's going to take this model that we've worked with. We didn't develop it; we got it from the literature. But he's going to take this model and bring it kind of into a visualization context. So develop a Shiny app around it, and then publish that app through RStudio Connect. We will have, after I'm done with just my real brief introduction here, we've got all the materials that we're going to go through today hosted up on our Metworks platform, and we're going to show you how you can get credentials for that platform, and you'll be able to log in. All the materials are up there. You can follow along if you want, and we'll show you how to do that just in a couple of minutes. So I'm going to just take maybe just another 5 minutes or so just to do this very brief introduction, and we'll let kind of any more people roll in before we actually get to the credential part. So this is content that was sort of started. We got invited out to University at Buffalo to do this for their CDSE kind of scientific computing days, and we've done this a couple of times. But we're really going to talk about optimization in R, or at least I'm going to talk about optimization in R. We know that this is so this is MRG Solve based. So we know that we've got people coming with different skill sets. Maybe you have used MRG Solve before, maybe you haven't. So usually whenever I do a workshop, I just start it with a very brief intro, just you can get the flavor of what MRG Solve is, and just basically how it gets used. And we'll see more and more of that as the workshop goes on. And then I'm going to go into like a series of vignettes where we're going to do optimization in R, and we're going to there's sort of a pattern or a way to do this in R that allows you to pull in different optimizers into your R code. And so we're going to talk about that. I'm going to start off to talking about just this R way to do optimization. We're going to do that in a context, just a very simple linear model. And so we're really going to focus on the mechanics of optimization, and that time is going to be an investment, so that when we pick up optimization in a PK model or a PBPK model, we'll sort of know how all those mechanics work. So we'll kind of do this R optimization simple linear model. We'll pick up just a simple indomethacin PK model, and then a more complicated DDI model, and that's the PBPK model. There's another vignette that's going to just take that PBPK model, and it's going to pull in just a bunch of different optimizers, and we'll show you how to do that. So for example, there's optimizers that are gradient based. There are different global search type mechanisms like or optimizers like a genetic algorithm type thing. And all these are provided by different packages. We'll show you how to connect those in to what into your model that's coded up in MRG Solve. There's also a little vignette on local sensitivity analysis. Usually I do some kind of sensitivity analysis before I start optimizing. We may or may not get to that because we got a lot to talk about with the optimization. Then, as I said, Devin's going to pick this up, and we're going to start to build and then publish a Shiny app around the model that we're talking about. So the optimization that we're talking about today, this is really just a single level of random effects. So these are sort of population, or they're just a single level of parameters. So we're not talking about models that are hierarchical models, no inter-individual variation or anything like that. If you did want to do that, there's options, other options that are available. You can use NLME. SAE mix is another one that'll let you do SAEM in an R context. And then I would highly recommend looking at NL Mixer for multi-level modeling in R with ODEs. And that's just another package that's I linked out here in the slide deck that you may have heard of. But really what we're talking about today is if you're doing PBPK modeling, if you're doing QSP type modeling, if you're doing simple PK optimization, or just kind of any optimization, I hope this will be helpful for you in R. So really briefly about MRD Solve. Again, I want this intro to be really hands-on based, and I'm going to do a short little code around MRD Solve. It's an R package, and really the idea here is we're using this to simulate from ODE-based models. It's free, it's open source, it's hosted on GitHub. You can get it on CRAN. Everything that we use MRD Solve for, you can use it for too, and maybe more. And everything's open. Your model is written in C++, and all that kind of hard work of solving the differential equations is done in C++. That makes it fast, but you don't really need to know C++ to do this. We won't really talk about model specification, but the way I say this is that you know, when you're writing your model in non-mem, if you do modeling in non-mem, you're sort of writing a Fortran pseudocode. So you kind of have to know a little bit about not Fortran, but you don't need to be able to code in Fortran. It's the same idea with MRD Solve. Your model gets compiled into a C++ file, and so you're kind of writing C++ code, but you might not even realize that you're writing it. But that's what makes it fast. And some of the other features are up here too. I won't talk about this. We've been doing this, I'd say, for maybe 10 years, and it just started, as Mike said, it just started off really simple, and we just said, man, we just need to simulate some stuff. So this started as an R front end to Dissolve that maybe you've seen. That's another ODE package available for R. And then it just grew up to where we started taking control over more of that simulation process. And we use it inside Metrum Research Group. I think I don't know, maybe we brought it public in 2014 or something like that. Maybe it's been 6 years that it's been out in the public, and we've sort of been publicly developing it and really wanted to push it out to the user community so that other pharmacometricians or other modeling and simulation scientists could use it. There's a lot of resources out there. I'm not going to go through all of this. This will come through in the content, but again, we're up on CRAN. You can go to our GitHub site. That's where all the source code is. There's an issue tracker on GitHub. I'm going to click through that really quick. That looks like this. If you make an account on GitHub, you can ask questions here, or you can file bug reports. You can also just view the source code that's over here. And so everything's public. Everything's open. I've got some resources here, mrgsolve.github.io, and that's where you can access things like a user guide. I keep a blog where I just kind of push up little vignettes when we come out with new features and that kind of thing. But there's a lot of content up there. You access it through this mrgsolve.github.io. And this is sort of that portal we've got documentation and examples all over the place, and you can access it through this portal. Okay. So that's my sort of get started, like welcome slide deck. And I think we want to, Devin, I think we want to go and kind of get people up and using get logged on if they want to. Does that sound about right?
Yeah.
Okay. So Devin, being the mastermind that he is, made this. So he made it so that you can, when you follow this link, you can sign up for short-lived credentials on our network system. This is going to give you access to an RStudio session and all the content in the workshop. And I'm going to just push this out to the chat if I can get there. and I think it's probably best if I just follow along here. So, so if you go into the chat, there's this URL, rnpharma.metworks.com, rsconnect/signup. And if you want to get at the content, if you want to look at the vignettes that we're going to walk through, if you want to follow along with what I'm talking about, and with what Devin's talking about, you can get to this content up here. It's going to bring you to this website where you can enter in your email address. And I can get a set of user credentials, and you can follow this link and to a sign up page. You can use this username, and then you can use this password here. So when you enter in your email, you'll get your own set of user credentials, and you'll be user 75 or something like that. So sign in with your username. Don't use user 35, that's mine. And that'll get you access to this. So I'm going to follow this through. I think I might need to.
We had a little dry run, so he's already signed in. But,
okay.
Hopefully, I see some people pinging. Some are getting in, some are getting not. While Kyle gets kind of going with the content, feel free to ping me if you're having problems and kind of explain what it is, and I can help diagnose.
Mm-hmm. Sounds good. So when you get logged in, you'll be on our network system. You'll get access to an R Studio Server Pro login, and you should see in your Files tab, you should see a directory called R Pharma PKPD 2020. And if you click on that, you will be in, well, you'll see at least the files in that directory. And this is all the content that I'll be presenting for today. All the content's actually in this content directory, but we've got this set up with a RStudio project. And it's pretty important that you open up this project. That's going to set the, it's going to point to all the packages that you'll need to run the code. And so if you click on that project link, and it's going to say, do you want to open this project? And if you say yes, it's going to open up that project, and it's going to pull off all this magic. That's going to set up your environment. That's going to, so that it will be able to find all the packages that you need. One of the things that you'll look for here is that it's going to set up our renv. And so that's basically going to manage all the packages in the R session. And if you just run this, the key thing here is that it's going to set the path to where all the packages are installed. So when you open up the project, that's going to get set off. If you want to dig into the content here, I've got all the content in this content directory. These are all set up as our markdown files, and they've been rendered to both HTML documents and markdown documents. If you want to go into this little gear here and just say set this as the working directory, probably not absolutely necessary, but this is sort of where all the content lives. And so if I open up this Rifampin Midazolam document, I'll sort of be working in that working document, or in that working directory. And then if you want to just follow along with like the vignette, you can click on one of the HTML files that we're working on, put it in View Web Browser, and then you should see like a rendered version of whatever it is that we're working on, and you can see the code and see the rendered output, and that might be the best way to follow along for the workshop.
Two final comments there. One, this is recorded, and so especially while we're live, I highly encourage kind of sitting back and focusing and listening and thinking and being willing to ask questions, because you can always go back and consult the video again, but kind of marking where those nuggets that you might want to revisit are. The other piece is we'll leave this up for at least a couple days, a week, so you can come back during downtime of the conference or this weekend or otherwise and play around then. So don't feel like if you're not playing around during the duration of the workshop, it's going to kind of go away. We'll keep it up for a bit. And again, all of this content is also on a GitHub repository, so you can also pull this into your own systems. And so again, just to me, the most effective thing is just to sit back, relax, enjoy, but if you want to follow along and kind of run the code as Kyle's going through it, feel free to do so.
Yeah, I mean, we kind of took a pretty big bite here when we got the content. Usually we would do this in at least a day and probably like a day and a half, or maybe two. We've done this in like 2 days before. It depends on how detailed you want to get. So this is really just a show, like a show and tell. Like we want to show you some things and get you pointed in the right direction for you to pick this up in your own work. So I'm just going to go for about 10 minutes and just do a really brief. So I know we got people coming from different backgrounds and different skill sets. I want to show you just a little bit of code that I'll get checked into the repo, but I'm just going to code this live about how to get started with MRGSolve. So as I said, MRGSolve is really about simulating from models that are systems of ordinary differential equations. So the typical models that we use for PK modeling or PKPD or QSP or PBPK, the basic workflow it looks like this. So in my R session, I'm loading tidyverse here, and I'm also going to load MRGSolve, and I'm going to check my working directory. Okay. The way the workflow works is that, and this is really the way to get started running MRGSolve, is that we've got some models that have been pre-coded for you, and you can access them, and they're models that you probably already know about. You can access those with a function called modlib. And I'm going to call this modlib function. Again, if you're not really used to coding in R, I can say $modlib, and that's going to give me the R help file, and that's going to show me all the stuff that I'm going to need to know about running modlib. And I'm going to point modlib to PK1. That's a one compartment PK model. And I'm going to save that to this object called mod. And once I've got that object called mod, I've got everything I need to run a one compartment PK model. I've got different parameters in the model that we're going to call with param. And this is going to tell me that I've got a clearance, I've got a volume, and I've got a Ka, and that tells you a little bit about the structure of the model. There's another function called init that tells me that I've got a central compartment, and I've got an EV or an extravascular compartment there. That number by the compartment name tells you that the EV is the first compartment, cent is the second compartment. And so once I've got this model object, I can really interact with it, and I can figure out what's going on in that model. I can also print this to the screen. That'll give me a little overview of some of the things we've already seen. So I've got my compartments here, my parameters. It gives me a little bit of information about how the differential equation solver is set up, and then as well as a simulation time grid. I can also see the model code. And this will just print where that model kind of came from to the screen. And we won't have any time, I don't think, to talk today about model specification. But I can just briefly just say that we've got a parameter block where we code in parameters. This is text that you write in a file. We've got a compartment block where we can specify the names of the compartments. Here I'm calling PK model, and I'm telling it that I want a central compartment with a depot compartment. And I've also got an output that's concentration. And that's just going to be the scaled amount in the central compartment divided by the volume of distribution. So just really basic PK model. And I can simulate this from this model, function called MRGSim. And I pass in that model object, and then it knows that it's got the structure of that model in there. It's got everything I need to know about simulating from that. You can see when I simulate from that, this is what that output looks like. I've got an ID column, I've got a time, I've got the 2 compartments that I had, and then I've got that that output, that CP right in the output. And we're getting all zeros here. I can take that because we didn't specify an intervention. So we didn't add any dosing, we didn't perturb the system at all. And the way we can do that is I'm going to just switch around to this pipe syntax here. I'm going to make this a little bigger so that we can see it. So I'm going to take my model object. So this is the same. So line 16 here is the same as the line 14. We're just using this pipe syntax where I take this model object. I'm going to pipe this into the MRGSim function. It's going to simulate from that model. Still, we're getting all zeros here. And if I want a quick way to add an intervention into there, I can just call this function called EV. Again, we can go to this help topic for EV, and it's going to tell us a bunch of stuff that we can put in there. But I'm just going to build this up a little bit. I can put a 100 milligram dose into the system. By default, it went to into this EV compartment, and now we're actually getting something, right? So we've dosed into my extravascular compartment. Now we've got a dose in the system, and that's distributing around, and we've got now some concentration or amount versus time profile. Just to make this a little bit more pleasant to look at, I can pipe this output. So by default, this output just sort of gets dumped to the console there. And I can instead dump this to a method called plot. And now we've got, taking our model object, we're adding a little intervention there, sort of on the fly. We're simulating on line 18, and now we're sending it out to plot. Now we've got, now we can see what this concentration time profile is. A little bit, we can do repetitive dosing, so I equals 12. Interdose interval, we can do an additional, let's see, just do an additional 9 doses. And I can run that code again, and now we can get repetitive dosing. And you might say, well, I thought you wanted so additional doses of 9. That means we want a total number of doses of 10. But we still only see 2 doses here, and that's because this. Remember this model object, that's we've got this internal time grid, so the object has an idea of when to start simulating and when to end simulating. We only went out to 24 hours here, and we can do this out on the fly, just to say, let's end it at 240 hours, and now we get all those doses. We can also, in the simulation time grid, you can see this. There's this delta parameter. That means that when I simulate, I want to get a simulation every 1 time unit, and you can kind of see that here. You can see that time is 0, 1, 2, 3, 4, 5, and we can say delta equals 0.1. This will give you a lot more data to simulate. Now we're getting a much finer time grid in the simulated output, and it's kind of hard to tell on this plot, but we get a much kind of smoother profile on that plot. And so we've taken this model object, we've added an intervention. This is the simplest way to do it with this event object to get a really quick simulation out of this model, and we've plotted it so we can turn that into a plot that we can look at to see what happened there. And you'll notice that we've only got a single profile there. And so I want to contrast this way of taking this model and sort of just taking a model and pairing it up with a an intervention that we can also just take a data set. I've got this meropenem data set. So there's a model that was up on DD Moore, and I really just took that out. And I can show you the reference for that, but hopefully this looks a little bit like maybe some of the modeling that you've been doing, where this is a data frame, and this modeling data set is in sort of an NMTran format. So we've got things like ID, time, DV, MDV, EVID, and that kind of thing in here. And I've got to head that off. So this is the same type of data set that you might pass into non-mem. We've also got things like age, so covariates on there, weight, creatinine clearance. There's a compartment and a duration. And I don't have the meropenem model up here, but I'm going to just load another model. I guess I can use that model still, one compartment model. Let's see. Yeah, I'll just show you this modlib PK2. So now I can get a 2-compartment model. Look at my parameters now. Now I've got a clearance KA. Now I've got V2, V3, and Q. So I've got more parameters in the mix. And I've got some more compartments. Now I've got a central and a peripheral compartment along with that extravascular compartment. And I've still got CP as the simulated output. But I want to pass this in. So we've got a bunch of people in this data set, so a bunch of different IDs. Data ID, EVID. And now we've got, with each individual, we've got some EVID zeros, which are observation records. We've got EVID ones, which are dosing records. And so the same way I took that model object and I just had this real simple event object here that just said, just do some doses for me. Now I can take this data set and I can pass in the data set, data, MRD sim. So now instead of doing that simple event, I can say I've got a whole data set of people that I want you to simulate. Yeah, actually, I'm going to redo this pop EX. Sorry. So pop EX, this is a population example model. I think this will be better. This has some population variability to it, but the idea here is that when I pass in a data frame full of people, I can plot that output, and now I get, because I had a bunch of different people in that data set, I get a bunch of different profiles out. And so I can take control of this plot a little bit because it's kind of messy. I can plot iPred versus time. And this gives you that meropenem data set. So it was just it was either a half hour or a 3-hour infusion. They just simulated out to 8 hours. Type equals both. And you can, I just kind of put some points on the different places where we had those. Oh, I know what's going on here. So this is a good, so yeah, so basically this dose was going into that extravascular compartment. Really, we wanted that dose to go into the that central compartment. But anyway, you can see that the points where I have the times where we have the points, that's where we've got observation records in that data set. And so when you pass in that data set with observations at just the times that you want to have those observations at, you'll get observations at those times. And so it's like you can take your non-mem data set, pass it in just like we did, or almost like what we did with this simple event object, and now we can do this population simulation. We can simulate batches of people at a time, or we can do just random simulations. And if you can simulate this over and over again, you can see we're drawing random effects from that random effect distribution, and we get different profiles every single time that we we simulate. So there's two kind of modes and of doing this. And when your simulation workflow in R is always going to be like coding a model. That's not what we're going to talk about today. But you're going to code up your model. If you're just playing around with MRGSolve, check out this modlib. You'll see example models that you can just get up and running. Simulate out some different dosing regimens to see how that works to get your intervention right. Then you might create like a data set here with a bunch of different people to do population simulation or simulation in batches. And this is just really the best way to, I think, to get up and running with MRGSolve. So that's sort of like just our basic workflow. We're going to see a lot more of this as we work through the vignettes. I want to switch to our PBPK example to get into that. We're going to see more of this, so we're not done with this, but I'll just take a really quick break here and stop and just ask if there's any questions. That if you could just jump, well, yeah, if you've got a question, can you just shout it out and I'll try and answer this for you. We'll kind of do this live here.
Looks like there was one in the chat box. Kyle, does it make sense for Devin and I to read it to you, or?
Yeah, if you could, yeah.
Devin, you want to take it, man?
Sure. So the question is, does it take the individual covariate values when simulating at this point as well?
Yeah, so it'll take the individual covariate values. Yeah, so and the way that works is that let me just close this off here. Oops. Let me close this. Okay, so in my data set, right? So just like in your non-mem data set, you put your covariate into that data set. And so this individual 1 had an age of 29.7. Individual 2 might be 40.2. Okay. I think these are just simulated. They've got their weights. If you look at the parameters in my model, so I didn't really match up the meropenem data set with a meropenem model, and I can put that in, but this does kind of work for this model here, is that you can see that I've got a parameter in the model called weight. And the idea here is that when you've got a parameter in the model called weight and you've got a column in your data set called weight, it's going to pick up those like really row by row. So these can be time varying or they can be constant with an individual. And the key here is that you've got a parameter called weight and you've got weight in the data set too. I'll point you to one other resource here because I suspect that there's a lot of people that like this is like really new. I've never seen this before. We've kind of gone kind of fast here. Part of my strategy here is to rely on repetition. So we're going to see this again. And so I'm going to try and reinforce this through repetition. If you do want to just get started from scratch, I put in this vignette called Get Started with MRGSolve. I did this as like a 3-hour webinar, and this is really just starts from the basics, and it's got a lot of commentary, it's got more code and more examples, and it's going to talk a little bit more through all the things that I've kind of talked about in this initial vignette. So you can take a look at that. Yep.
So I'm in the contents folder. Is the get started.r markdown the right file for us to work through initially?
Yeah, so the get started is something that I put in there for you to, yeah, you can start working through, but that's really like homework.
Okay, good.
Yep. Yep.
Awesome.
Yeah.
So that's
yeah.
Got it. I'm just trying to figure out, is there a file in that folder that we should open up or not?
Right. Yeah. So that's your homework. You can look through that vignette. It's going to tell you more about the types of things that I've been talking about in this really just little code around Scratch document.
A+. Oh, awesome.
Yeah. Okay. So so we've got this kind of workflow where we're going to code up a model, we're going to read it in, we're going to come up with some intervention, and then we're going to take a look at the output. And we're going to just see this again. So I want to switch to this document called Rifampin Midazolam DDI.RMD. And this is just like, we're just going to explore this PBPK model with MRG Solve. And I've got the reference up here. This was published in CPNT PSP. It's an open model. And so they did a really nice job of like publishing all the code underneath the model. And if you go into this model directory in your checkout, and if you go into rifampin.pdf, this is that. So you can get this through the link through PubMed. I just put it into the repository here so that you can just click on it and it'll open up. There's another PBPK model that wasn't it's not open access, and I didn't include that, but I'll show you that model, and you can get the link to that. So if you have access to that journal, I think it's in just CPNT, the main CPNT. So we really want to do this optimization in a PBPK type context. So I just want to do a quick code around with this model. They're really looking at interaction between rifampin and the drug that I'm going to look at is this drug interaction between rifampin and midazolam. And so we're going to, the same way we opened up our one compartment model, we opened up that two compartment model for a minute, and then I switched over to that population example model, which I think is just a two compartment model. The model that we're going to be looking at in this vignette it's these two models here. So model A is for rifampin, and then model B is for midazolam. And in our model file, we've got both these models going at the same time. So these are PBPK models. We've got two muscle compartments, one for rifampin, one for midazolam. We've got two skin compartments, one for rifampin, one for midazolam. You get the idea. And all of these are coded up, and the authors kind of published all this code, and they made it reproducible. And I think we've been able to reproduce a bunch of their figures. But I just want to do a quick walkthrough through this model. So on the rifampin side, we've got kind of the standard Pvk modeling compartments. These authors like to use this 5-compartment liver compartment. So this is the liver down here, and you've got HE, which is hepatic extracellular, and there's 5 kind of a transit compartment system. You've got HC, which is hepatic intracellular. And so as the rifampin makes its way and it distributes into the liver, it goes through this transit system. It's able to transfer in and out of the liver cells. Inside the liver cells, it can get eliminated there. And then there's also this an OATP transporter. There's this active transport. You can see this PS act int here. That's sort of an active transport process. So you've got kind of bulk flow in and out of the liver cells, and then you've got this OAT mediated active uptake into the liver cells. And then all this elimination is happening in these HC compartments. So it's kind of a complicated model here, and they've got some kind of interesting modeling here in the gut lumen and enterocytes and that kind of thing. And we won't be able to get into that. On the midazolam side, it's a little bit more simple here. Again, they got just a simpler liver model where they got this 5 transit compartments and then elimination from inside the liver. So we got all this going on in this model, and this model is coded up in this model directory, and it's in this file called rifampin midazolam. I've got the links and the reference up there, but you can see that this is almost 400 lines of code. We've got a set of equations for midazolam here, and then a set of equations for rifampin, and we're going to look at a couple different aspects of this PK, the rifampin and the midazolam with this model. So we had that really, really simple one compartment model where we just loaded it up with modlib. Now I'm going to load this model up with a function called mread. So our modlib function was a little light wrapper around mread. Mread's going to look at in this model directory, and it's going to look for rifampin midazolam in this file here. It's going to load this up, and now I've got that huge PBPK model loaded up into my R session. So I've got all these. I've got 41 compartments and 61 parameters. I've got 3 outputs, central, which is rifampin, and then C midazolam, which is that concentration of midazolam. And we can look at the same way for that simple model. We can look at the parameters. This gets to be a little bit of a mess because there's so many of them. Compartments, again, this is a little bit less helpful because it's a little bit harder to get on top of things just because there's so many compartments in there. But I can just interact with this model in the exact same way that I did before. So rifampin, they did a 600 milligram dose, and I can just kind of make it an event object the same way we did before. I've called this rif, and now I'm going to put 600 units into compartment 1 at time 0. And I can work this same, here, let me just edit, clear all output. The same simulation workflow. I can take my model object, I'm going to point it at that rifampin kind of event object there. I'm going to say I'm only really interested in this C central. That's what request means. So request just says I only want to see C central on the output. I'm going to simulate out to 48 hours. And now when I plot this thing, I got my rifampin single dose PK profile there. So much more complicated model. In fact, 2 of these PK models going on at the same time. But the simulation workflow is exactly the same. We just put a dose into a compartment at the time that we want. I can mutate this event object. So now I'm going to say, instead of a single dose, I want to do daily dosing for 10 days. And I can simulate that output, and I'm just going to plot this C central versus time. This shows you how we can coerce this output to a tibble, and I can plot this with ggplot, or I can just look at this is a lattice-based plot. But you can see that the exposure seems to be going down over time. At least the Cmax is going down. It's a little bit harder to tell in terms of the AUC. So I want to investigate what's going on here. So I'm going to take this output. I'm going to mutate this. I'm going to convert time into a day. So I'm just going to take floor out of time divided by 24. I'm going to group it by day. I'm going to calculate an AUC every day. Sorry. And that'll give me a data frame of AUCs. And so for each day, I've got a different AUC, and what I've done is I've kind of calculated this additional output called PAUC, and that's the AUC, that's a percent of the day 1 AUC. And so for day 1, AUC is going to be 100. And as you can kind of guess, as we go increase dosing, or so remember doing once daily dosing, the AUC, once you get out to day 7, it's down to not, you have almost a 30% decrease in the rifampin AUC after kind of repeated rifampin dosing. So that tells you, you'll see this in the paper, that a rifampin it auto-induces its own metabolism. So rifampin is going to upregulate UGT, and you can see by the time we get out to day 7, we have not quite double UGT metabolism, and that's causing a decrease in the rifampin exposure. So we got increased metabolism, we got decreased rifampin exposure, and so rifampin is auto-inducing this, so it's inducing its own metabolic enzymes. You'll also see on this plot that we've kind of have a huge increase, fold induction, almost not quite 4-fold induction of CYP3A4. And that's really the basis for this midazolam drug-drug interaction. So I can make another event object with midazolam. Here I'm going to put 3 milligrams of midazolam into this M-gut lumen compartment, and I can simulate from this and plot. That's our midazolam profile, just a single dose. And now I'm just gonna, I want to simulate out this drug-drug interaction. So I'm going to do, what I'm going to do is I'm going to do 7 days of rifampin at 75 milligrams per day, and I'm going to put that into that gut lumen compartment. And now I'm going to put these in a sequence. So I'm going to take, I'm going to say, do that rifampin sequence, wait -12 hours, and then do the midazolam. So this is what happens. So I'm going to do 7 days of rifampin dosing, and then 12 hours after that last rifampin dose, I'm going to give a dose of midazolam. And now I've got this in a more complicated event object, and I want to simulate both of these. So I'm going to do my both. And now I've got 2 individuals in that event object. I've got 1 individual that's just getting midazolam. And then 1 individual that's getting midazolam after the rifampin. I might need to run this from the start here. I want to make sure this is going right. Okay. So now I can do my same simulation sequence, take my model object. I'm going to simulate out to 166 hours, and I'm only interested in that midazolam concentration, create those simulations, and then look at here. And I think I need to go back. And do this 155. Sorry. I did something here to botch this up here, and I need to simulate this out. Sorry. Okay, so this is really what I wanted to do. I want to get that matching midazolam concentration right at the time that that rifampin is done dosing at. I think I just botched this up last night. So yeah, let's just get this in here. Run this out. What the heck did I do here? Okay. Now we're gonna go to the oven here. Oh, this might not have gotten done properly either. Let's see if this did do it. Yeah. So I botched something in the code there, and I'm not going to try and kind of fix it on the fly, but I'll just kind of show you what the upshot is here. So right, so we've got in the green we've got just a single midazolam dose, sort of without any rifampin on board. In the orange we've got midazolam after rifampin. We can see that after this huge induction of the CYP3A4, we've got a much smaller rifampin exposure. This is on log scale, so this is quite a bit. I can take those simulations. I'm going to group it by ID. I'm going to calculate that same the same idea. Just calculate that AUC with the rifampin, or sorry, the midazolam alone, and then the midazolam after rifampin. And we actually get a 72% reduction in that midazolam AUC after rifampin compared to midazolam with no rifampin. So just to show the magnitude of that drug-drug interaction. And then we can I've got another workflow here to show, we wanted to just do some R code to just look at, that midazolam AUC after rifampin just as a percent of no rifampin, and we can run that out as a function of dose. And to say, like, as we kind of increase that rifampin dose, we get out to this highest dose, and we get to like almost a 90% reduction in that midazolam AUC when we dose at the 600 milligram rifampin dose. So that gives you like a little flavor about how that the same simulation workflow in this kind of context of this more complicated PBPK model. And hopefully we kind of reinforce some of the things that we did in that initial code around when we got up and started, and I kind of hope you kind of got a feel for just this idea that kind of regardless of how complicated the model structure is underneath, your simulation workflow in R it's about the same thing. It's really just taking that model object, creating your inputs. If you didn't botch it up the way I did here, creating the inputs and then simulating from either that event object or that data set. So that's sort of like our MRG solve, just coding around and just gives you a feel for how things work. We really wanted to let MRG solve kind of leverage the tools that you already have available in R. So we were using things like filter and group by and all that kind of stuff. So all MRG solve doesn't actually simulate or it doesn't actually process your data. All it does is simulate it, and we just rely on great tools like dplyr and ggplot to handle things after that. Yeah, so I'm just going to take a quick break here, or just a quick pause. I'm going to do a quick water break and really kind of shift gears here. Phil or Devin, just please, or Mike, please hop in if there's anything coming out. I see there's some stuff in the chat, and I just can't access it really easily. But just let me know if there's any pressing questions in the chat, and I'm just going to keep trucking here.
Yeah, for sure. One just came up about the recorded video, and I shared the R and Pharma YouTube page where we're going to add some of the recorded videos. But one thing to keep in mind, about half the workshops were recorded and the other half weren't. So the ones that we're recording, we're hoping to put here in Metrum. I wasn't sure if you're going to store it on your website or something like that, but either way, you should be able to get to it.
Sounds good. Okay, so I'm going to switch to this vignette called Tools Optimization Intro. So if you want to follow along in that HTML file, that will give you the sort of the rendered code here. And we're going to, for the next like 20 minutes or so, maybe, we're going to leave MRG solve behind. And I just want to talk about the mechanics of optimization in R. And it's going to be with a really simple model that's going to be it's going to be a simple linear regression model. We're going to do optimization in R with a linear model, so trying to take the complexity out of it and just really talk about the optimization in R. I'm going to do this. I'm going to use this Swiss this data set called Swiss that comes with R. You can just call data Swiss, and I'm going to just make a plot of these are the columns: fertility, agriculture, examination, etc. This was generated around 1888, and these data were collected from 47 French-speaking provinces. The columns that I'm going to look at here from the Swiss data set are called examination and fertility. So fertility is like a fertility score, like how many kids did you have, kind of thing. And examination is, what they did is they took out of all the people enlisting in the Army, they took the fraction of people enlisting in the Army from each province that got like the highest score that you could get. And so the idea here is that as the people did better on the examination, the fertility score went down, or you can think of it the opposite way. The worse they did on the examination, the fertility score went up. So you can kind of hypothesize about what's going on there. But I thought this was just a really simple data set, and what we're going to do is we're going to do linear regression on this data set in R. And I just want to emphasize that the real way to do this in R is a function called LM, and that will give you a linear fit to this data. It'll give you the intercept which is 86.8, kind of back up here, and then the slope is just around -1, right? So it's a negative slope, and it's giving us -1. So the answer to this linear model is really, it's a closed form solution. This is the right way to do it. If you're just interested in doing linear regression, we're really interested in learning about optimization. And so I'm going to try and do this linear regression as an optimization problem in R. And this is how we're going to evaluate what these different tools are and how they work. And so I'm going to propose a model for this data. The parameters are going to be the intercept and the slope. And I'm going to do a simple linear regression. So I'm going to call EX is going to be that examination, right? So this is my predictor. I'm going to regress fertility on examination using this Swiss data set. And to do this, I'm going to make this a little bit more, probably a little more complicated than it needs to be. But the reason why I'm doing this way is because this is going to help us optimize when we get to R. So I'm going to make a function called linear model. And this function really just takes in an intercept. It's going to take in the slope. It's going to take in the predictor, and it's going to return what is going to return the fertility score, right? So I'm going to take an intercept and slope. I'm going to take in my examination, and I'm going to calculate the fertility score. And this is why we're doing this. It's just really, really simple. But I can call this linear model function, and I can pass in my slope and intercept and a different exam score, so 20% of the people got the highest score, and I can return to get the fertility score is going to be 50. And so I'm really thinking about a model that returns a response from a certain set of parameters and a certain predictor. And I'm going to pull these out of that Swiss data set, X and Fur. These are just going to be just vectors of data. I'll show you the way that I'm going to do this with MRG Solve when we get to that in a Methodson example. But I'm just going to do this just to simplify things a little bit first here. And so now what I want to do is I'm going to take I'm going to kind of one up this a little bit, and I'm going to create another function called my objective function, or OFV, or it's a function that returns the value of my objective function. So I'm going to take in a set of parameters. It's going to take in my predictor, and it's going to take in my response variable. And what I'm going to do is I'm going to get a prediction from those things. So part 1 is going to be intercept, part 2 is going to be slope, and I've got my predictor here as example. Remember, I just had that linear model function that I can call. I've wrapped that up. It's probably more complicated than it needs to be, but I wrapped that up. But I want to show you that I'm going to generate a prediction based on parameters and predictors, and I'm going to return, what is this? I think we know what this is. This is the sum of the squared residual. So I'm going to take the residual here, fertility, minus the predicted value. I'm going to square it. I'm going to sum it up, and this is my OLS. Yeah, squares, I guess that's supposed to be like that. So this is my OLS objective function. Okay, so now I've got a function to run my model. I've got a function to test a set of parameters to see how well they generate predictions that are close to my data. So this is what I want to do here. I want to say, like, I think the intercept is 70 and the slope is -2. And I can turn that crank, I can run that through my objective function, and you'll notice that the objective function returns a single value, right? And so when we're doing an optimization, we want to get a function that returns one value, and this just quantifies like how well 70 comma -2 fits the data. You remember how what our, not the linear model, but that I'm going to scroll back up here. So the real values are 86 and -1. So I kind of pick some values that were kind of off there, and I might say, well, is that good or bad? Well, I don't know. Let's try that. We know that the real slope is a little bit close. It's 86. It's a little bit closer to 80, and I can turn that crank, and now Under a different set of parameters, I've got a different objective function value. So now instead of being 58,000, it's 32,000. Wow, we got a little bit better there when we tweak the intercept there. -2, we know that's off. Let's bring it down to 1.5. And I can do the exact same thing. And now I've cut that objective function value in half. So now instead of being 58,000, now we're at 15,000. Okay, this is a lot better, but we can't keep on going like this. We can't just keep on guessing what those parameters are. And we might just say, let's make a grid of parameters that just looks at a bunch of different intercepts, looks at a bunch of different slopes. And I'm going to just run this through my R code. And I'm going to make this, so for each pair of intercept and slope, I've got a value for the objective function. And I've arranged this so that it gives me the one that has the lowest objective function and that had an intercept of 87 and a slope of -1. Not bad there. And I can make a contour plot of slope versus intercept. You can, and this is like kind of going down so that our lowest value is somewhere right in the middle here. There would be a dot there. And this is really kind of telling us that like we're kind of honing in on what the real value is, right? But even then, like this is still like this brute force, and we can't keep on going like this either. We really need to invoke the help of an optimizer, and that's really where this power of R is going to come in. And so R comes with an optimizer, and there's a lot of other R packages that will provide different optimizer functionality. And so instead of searching a parameter space like this, where we're just going to guess a bunch of intercepts and slopes and then find the one that gives us the lowest value, we're going to like thoughtfully explore the parameter space. And we do that with R comes with a function called optim. It comes with a couple different optimization methods. By default, it does a Nelder-Mead optimization, and this is where we get to the pattern here. Okay, so this is where we're going to see this pattern is that we've got a set of initial values. I'm going to start my guess. We always have to guess where it starts at. Is going to be 101. I've got my objective function. Remember, that's the thing that turns parameters, a predictor, plus my dependent variable into some number. And I'm going to pass those in. And Optim is going to go through and it's going to generate some parameters that gives me the lowest value of that objective function. And it's going to give me, frequently when you run an optimization, it's going to give you back a list-like object. Frequently, your final estimates are going to be in par. So this gave me 86.822 and -1.11. And if we compare those to the fertility examination, that kind of that real linear regression, the way that we want it to do it, it gives us pretty close. Obviously, the LM it uses, there's a closed form solution for this, and so there's just one answer. When we do the optimization, the optimizer doesn't know about that closed form solution. It's searching this parameter space. Once it gets to the lowest value within a certain tolerance, it's going to just say, hey, I've reached the minimum here, and I'm just going to return it. So it's not going to give us that exact answer, and I can probably get closer to that exact answer if I just asked for like a smaller tolerance. But for now, we're going to call this is pretty good. We really went from a pretty bad guess, or I guess I can make this worse, like a pretty bad guess to a pretty good final solution, final answer there. That's getting us close to what we know that true value is from the linear model function. Okay, so again, I wanted to emphasize that this is like a pattern, and so there's a bunch of different optimizers that we can call in. One that I like to use is from this package called MinQA, and there's one called NewUOA. And so this is just another optimizer like we had for Optim, and the pattern's the same. I have theta, which was my initial guess, I think. Oh, maybe I didn't have. Oh yeah, yeah, that was an initial guess from above. Yeah. So the pattern is you pass an initial guess, you pass in a function for R to optimize. These other arguments get passed along to the objective function value. And then usually there's some kind of control parameter that will let you control different aspects of the optimization. But I've kind of asked it to print out some extra details here just about how the optimization is going along. If you run non-mem, this is sort of like watching the iterations on your non-mem run. We start with a function value that was 15,284. So remember, we had that value from above, and this objective function value is going to decrease pretty rapidly down to that final value, which was 4183, and then we can see the value of those parameters as they move toward that smallest objective function. And when we do this, we get the same answer essentially. So that's one optimizer that comes with our one optimizer that came from outside of our, or it's just an R package that you have to download from CRAN. For global optimizer, I like to use a package called DE-Optim. I wouldn't use it for a linear model for sure, and I probably wouldn't use it for a PK model, but I use this quite a lot for QSP modeling. This is, it's like genetic algorithm. So it generates populations of parameters. It generates predictions from all the members in the population, and then it saves one member of the population to go on to the next iteration. Then it's the parameters mutate and that kind of thing, and then you eventually, like, the system evolves so that you get a really good set of parameters. Because this is a global optimization, we have to set upper and lower bounds. And so for my intercept, I'm gonna let it go from 0 to 1,000. Slope is minus 100 to 100, and I can just run this. This runs pretty fast because the calculation of the objective function is pretty cheap. But you can see that by the time I get to the end, the best value, so the best parameter set in the population had our objective function value of 4183. And then we've got our final parameters down here. And the idea here is that we kind of just used a whole different way of searching that parameter space to get to that same set of final parameters. We'll switch to maximum likelihood estimation. I can make a function called ML. That's going to do the just like what I did for the OLS objective function. I'm going to generate a prediction. Now I'm going to send that the observed data. I'm going to send the prediction, and then I've got a third parameter now called P3, and that's going to be my residual error variance. I can send that into dnorm. And so now I've got maximum likelihood. So dnorm is the normal likelihood function. I can pass in the mean, and then this will be the standard deviation. I'm going to ask for this to be log equals true, and I'm going to return -1 times the sum of the log likelihood. So that's going to be the joint likelihood of all the data. And then I can test this function out again. I'm going to propose a slope, an intercept, and now I'm going to have to propose a standard deviation. I'm going to have to say what that residual error variance is, and I can just turn this through that function called ML. Now I get the value of that likelihood function at this set of parameters. And so now I can go back to that new UOA optimizer, and I can pass in theta, and now I can appeal to this maximum likelihood function. You can see how much code we're reusing here. You get the exact same answer. Now we just got that third parameter, which is that residual error variance. And I can check the final value of the objective function. This is going to be different than our OLS objective function value. I just coded this here. You can do extended least squares. This gives you like literally the exact same answer that you got when you did, if I coded this right. Maybe I didn't code it right. This should give you the same answer as you got for that the maximum likelihood. So extended least squares, and the idea here is that, like, I like this kind of paradigm because you can really choose, once you get the simulation down, you can choose what the, you can choose what objective function you want to do. Do I want to do OLS? Do I want to do ELS? Do I want to do some kind of other type of objective function? You can pick the one that you want there. Maybe I just didn't, yeah, well, anyway. I can get the standard error of the estimate. So there's a package called numDeriv. It'll give you, it'll take the Hessian. So that's the second derivative of your objective function with respect to the parameters. So I can get that Hessian. We can invert that. So I'm going to take that Hessian matrix. I'm going to invert it here. I'm going to take the diagonal, and then I'm going to take the square root of that, and that'll give us the standard error of our estimates. So this is kind of a simpler thing that maybe NAMM does. It kind of has a little bit more sophisticated standard error calculation. This is a really simple way to get a standard error estimate from your model, and I can pull the estimates that I get from just a basic linear model, and it gives me something that's pretty close. I think this gives me some kind of scaled version of the standard error. But you can calculate that Hessian with tools that are already available in R, and then you can drive that standard error this way. There's also a function called FD-Hess that will give the Hessian by finite difference. This gives you the same thing that we got from the numDeriv. But again, we just take that, call that, this will do this finite differences. We pass in the final estimate. So we want to evaluate the likelihood function at the final estimate. We have to pass these along to that function, and we can get an estimate of the standard error. And then I can just make like a data table, a parameter table, where I can just take the, oh yeah, sorry. So that's my estimate, that's my standard error. I'm just gonna take, I'm gonna make a new data set where I'm gonna take the exam scores, the fertility score, and I'm gonna make a column called pred, and I can just call this linear model. I'm gonna take that final values. So the intercept and the slope, I have to pass in that exam score. And now I've got this data, and I can just plot that, bingo. And now I've got the fertility score versus examination. And in that red line, I've got my model prediction coming from that optimization. Okay, before you try optimization, your PK model, I'm not gonna do this now, but I had the simulated data set where I've got some other data. I've got some PD response that is some kind of anonymous PD response versus AUC. I can calculate, I can propose the model, and I can optimize some parameters that will fit this data. That's sort of like your homework. This is the first thing you should do before you start optimizing your PK model. Okay, so that's my whirlwind sort of run through optimization in R. We're going to see all this when we go to our endomethacin model, and I'll stop and just kind of pause here to take any questions about the stuff that we worked through here. Okay, so the next step that I'm going to do is I'm going to take all that stuff that we did with that linear model, and I'm going to take up this endomethacin PK data set. This is another data set that I think comes with R. It's called endometh. And we'll take a look at this. So this endometh data set, it's got subject ID. There's like 4 or 5 subjects in there, and it's got a concentration versus time. Yeah, how many did we do? Yeah, there's 6 people in there, but the data looks like this. So they gave an IV dose of endomethacin, I think. Maybe they did, maybe they didn't. I'm going to do this as an IV dose, whatever it is, and I'm going to just assume the dose that they gave. And that might not be documented in the data set. But this is just endomethacin concentration, single dose. We're going to do this as a naive pool analysis, and we're going to use emergy solve to to fit this model. So what I did, kind of pulling this out of the oven, is that I took that endomethacin data set and I sort of got it sort of like non-mem ready, or like a non-mem like data set, where for each individual I put a record at time 0 where we administered a dose of 25 milligrams into the central compartment, compartment 2, and we did this EVID1. Concentration, I've set this to missing, which is really, really important. For a reason why I'll show you in a second here. And so I can, I've got this data set, and I took the time to put this data set together. So I got everybody's concentrations lined up, ordered by time. I've got the dosing records in there. So a lot of what you see with MRG Solve is that we want to make it really easy to simulate things, and the times, I don't say they're not meaningful, but we just say, yeah, give me this grid of times, and that kind of thing. When you're doing optimization, I would really recommend taking the time to do the same type of data assembly that you would do if you're running non-mem. So get all the people lined up, get the concentrations at the right time, get the dosing records in there, so that I can just simulate from this data set here. And I can just take my model and I can simulate from that data set. So remember that first code around we had, we can say I can get a model and I can throw this data set at it, and I can simulate out this data set, right? So we can do this. I'm gonna try out a 1 compartment model first. And the idea here is that I can look at the parameters in that model. I've got clearance, volume, and Ka. And so I'm gonna pick some parameters to optimize from that model. And again, and just like that question about the covariates, I want to name these parameters to be the names of name my initial estimates to be names of the parameters in the model, so that when I go to update those parameters in the model, I've got the clearance is going to get translated into clearance, volume into volume, and then when we simulate, those things will match up. I almost always optimize these things on log scale. So I've just taken my initial estimate, I've put them on log scale, and they've got a certain name to them. So I got my data, I kind of propose the model, I've got some parameters in my model, and those are going to match up with parameters that I'm going to optimize, and now I've got my objective function, and this is going to be my OLS objective function. We're a little bit more complicated here, but this is why I sort of spent that time in the linear model. But the idea is the same thing. I've got my objective function that I want to turn parameters and like data into some objective function value. And this is a little more complicated, and I'll walk you through the other steps. This is really like a lot of the optimization with MRG Solve looks like this. And so I'm going to walk you through what happens here. So the first thing that you always get, the same thing with the linear model, you get the optimizer is going to search the parameter space, and it's going to propose a set of parameters. And our job is to turn those parameters into predictions and then see how well those predictions correspond to our observed data. So the first thing that I'm going to do is I'm going to name those parameters. So I'm going to pass in that theta vector, right? Theta had some names to it. I want to attach those names onto my parameters, because the names and the parameters kind of match up with names in the model, right? We need those to match up. Next thing I was going to do is I'm going to get my parameters out of the log domain. So I'm just going to lapply across there, call that, get those back out of the log domain. I'm going to call a function called param. That's an MRG solve function. It's just going to update this model object to take on these new parameters. So the optimizer is going to propose a next set of parameters, and I need to get those into my model, so that when I simulate from that model, and I'm going to simulate with my data set, I'm going to get outputs or predicted concentrations that are based on those proposed parameters. I've got a little trick here that I'll show you what this does. Pred is going to be false unless I tell it to be true. So I can just say I can opt to just return a prediction. And I'm going to do the same thing I did in the linear model. I'm going to take my predicted values, compare them to my observed values. I'm going to square that, and I'm going to take the sum the squared residual. I'm going to call NARM here to say that's true. Remember, in our data, I don't want those dosing records to affect the value of the likelihood. So I called concentration. I said it's NA on a dosing record. So when I say when data is on that dosing record, the sum of the squared residual, or the squared residual, is going to be NA, and then the sum, those NAs are going to drop out. That's the trick here. So always make dosing records or any data that you don't want to affect the value of that likelihood or the objective function, make those NA. We can do the same thing that we did with the linear model. I can just run, always do this first, is that run your initial estimates. This looks kind of funny because I'm going to do my initial estimates. I also need to pass theta through just to get those names. But at our initial estimates, the value of the likelihood function is 33.6. And I can do the exact same thing. I can go back to Optum, do that Nelder-Mead optimization. It goes pretty quick. These are my estimates on log scale. And then I can go back and I can use this to generate a model prediction. So here I'm leveraging that fact that I've got my objective function. I can pass in my final estimates, can pass in everything else I need, and now I'm going to hit that switch to say pred equals true. And now I've got a head pred. Now I've just got a prediction from my final set of parameters for my observed data, and I can make this plot. I'm plotting this on log scale, so I'm plotting my observed data here and my one compartment prediction there. Shoot, that didn't work very well. So if this was a class, I'd send this back to you and then ask you to, okay, what would you do next? Maybe we might try a 2-compartment model. I thought it was kind of interesting that the optimizer like totally gave up on these points down here. It just only went for those, so it didn't split that difference. And so I think it maybe it might even need some weighting there. But I'll just pull this out, and I want to get to the PBPK model. So I can pull out a 2-compartment model. That's PK2. Again, I'm just relying on that modlib, that internal library of models. Looking at those parameters, now my parameters are called, I still got CL, now I've got V2, V3, and Q. And so now my initial estimate is I'm gonna have to propose 2 clearances and 2 volumes here to get that theta. And now I can do that optimization again. Again, it's the same pattern. We pass in some initial estimates. I pass in my objective function to optimize, and then I pass in that other stuff that that function needs. I can always go back and appeal to that objective function just to get a prediction and pass that along. And now, once I do that 2-compartment model, I can get these estimates. I can get a much better prediction to my data. I still thought this was kind of interesting that I thought it could do a little bit better. So I'm going to create a new objective function here. This is going to be a weighted least squares. All these pieces are the same. I take my parameters, assign names, get out of log domain, and then take those parameters, use that to generate a prediction. And now I'm going to do a weighted least squares. So I'm going to take that weight to be whatever I want it to be. I'm going to take that residual, weight it, and then square it, and then sum it up. And then here, I'm going to do this fitted weighted least squares. Oops, I need to run that first. My DV is just my concentrations. Now I'm passing weight through there. See how that works? So weight here, and weight's up there. And then my objective function, we can, now we can, this is kind of the other nice thing about having this little pred trick here, is that I can go through and I can take, I can get a prediction at the final estimate. Pred I is going to be the prediction at the initial estimate, and then I can get the prediction from the weighted least squares. And then I think I probably didn't do that quite right. I think the weight needs to be just 1. And I can plot all these together and bingo. Okay. So now I've got that initial estimate in green. I've got that, and the gray is that kind of ordinary least squares, and then that red is that weighted least squares. And I think that weighting kind of makes sense to what happened here. I'm not going to go into this next section here. Anyway, I gave you a bunch of different options here for different global search algorithms. That's not going to get rendered in the vignette, but I'll, for example, show you how to use a global search algorithm to fit this indomethacin data set. And again, it's not that much different than you pass in your objective function, again, upper and lower limits, initial estimates, pass all the data through, and really all that work that we did to set up that objective function gets reused, and now we're doing global optimization instead of the more gradient-based methods. Okay, we're going to do the same thing with the PBPK model, and I want to take just a second to go through this model with you. This is the model that's, it was published in CPNT. They published all the code, quantitative analyses of hepatic OATP-mediated interactions between statins and inhibitors. This paper was kind of nice. Part of their purpose here is to show how they did optimization here. And so they kind of not only shared all the model code, but they shared like details about the optimization and that kind of thing, and that made it really easy to follow. You don't have this paper in the repository, but you have all the code, and you can go out to CPNT if you have access to this journal. And I just wanted to make a couple points. So this is the same group, I think, that did the Rifampin model. And so the model looks the same. I'll say that in a second. But again, like part of this paper, which was a kind of nice case study, I kind of like the way they wrote this up, as they looked at this optimization workflow. So they had clinical data of the DDI, they've had the substrate, they had the inhibitor, they had the substrate in the presence of the inhibitor, and there was like this sort of 4-step, or I'd almost call it 3-step workflow, where they took this substrate, which is the statin. We're going to look at pitavastatin, and they looked at different PBPK model structures. They looked at what the initial estimates might be, what are the parameters that we might optimize here, and then they really optimized that with that, just the substrate alone. Again, that's the statin, or we're going to do pitavastatin. Then they looked at the inhibitor. We'll look at cyclosporine. There's another model development path where they kind of looked at that alone. What should the model structure be? What are some parameters that we could optimize? And then they got those two models kind of going separately, and then they brought them together, and they optimized all the parameters together, including this Ki parameter. That Ki, that inhibitory Ki value is gonna kind of says like what that DDI is, and I'll show you where that comes up. And then they did it all. There's like their step 4, where they kind of put all these together into the same sort of big model, and then they can optimize that Ki for that inhibitor against that substrate. This model is really focused on that OATP, and I'll just take you through kind of where that is in the model. Again, there's just like a tons of stuff going on in this model. So the statin model, it's got this we're doing the one with enterohepatic recycling. Again, it's just like the standard PBPK model with muscle, skin, and adipose, and then this central compartment, that's sort of the more standard part. Same group, so they like to do this 5-compartment liver model, which the drug distributes into the liver, and it's kind of get through this transit system. We've got the extracellular, like outside the hepatocytes, and then we've got the kind of the key to this whole model here is right here, and this is, we talked about this a little bit in that first model, is that you've got bulk flow like into the hepatocyte, and then you've got elimination from the hepatocyte, and then you've got this PS Act, which is that OAT-mediated transport, kind of active transport into the hepatocytes through that OATP, and that's right where the cyclosporin. So we've got statin in this PBPK model, and we're going to have cyclosporin inhibiting that OATP, and that's happening right here. They also have this kind of distribution into the bile and like recirculation back into here. I didn't look at the one without the enterohepatic recirculation. So that's the statin model. The key here is OATP mediated this uptake into the hepatocyte. Cyclosporin model is a lot simpler. But again, they've got this 5-compartment liver model, and then just sort of bulk flow into that liver, and then you get less detail here in this cyclosporin. But again, the cyclosporin is running. We're generating cyclosporin concentrations. Those are going to act at this OATP by this Ki that we're interested in estimating through this model estimation procedure. Okay, so that's sort of the basics of this model. And again, like the Rifampin model, like we've got both these models going at the same time. I'm going to open up now this vignette called Tools Optimization PBPK DDI, and this is just going to be like our it's just going to give us it's going to be like that indomethacin vignette, but we're going to really look at this more complicated PBPK model. So I'm going to open up this here. Oops, I got to do all this too. Set the seed and some theming here. Okay. Here's the reference up in here. I've got the data file tucked away in here, and I'll show you really quick what I did here. Yeah, I should run you through this. Cyclosporin concentration versus time, just cyclosporin on its own. We can simulate that to this dashed line is cyclosporin in the liver. Basically what I did here is I took like one of these profiles, maybe B, and this is what the DDI looks like. So in the blue is pitavastatin alone, and I just digitized these points. We're going to optimize against these open circles. Blue is pitavastatin alone. Red is pitavastatin like an hour after cyclosporin was administered. And so you can see like these are plotted on log scale, but you can see the increase in exposure after that after the cyclosporin dose. Sorry. And so I digitized those data, and that's in that data set here. Again, I digitized the data and I put those into this sort of like non-mem type format where ID2 is going to get the statin plus cyclosporin. I've got a dosing record here at time 0 where they get cyclosporin. This is this is really micrograms per kilo, and then 30 milligrams of the pitavastatin. And just to filter out just the dosing records there, so you can see ID2 is going to be the statin plus cyclosporin, ID1 just going to be the statin. And I can just plot this out just to do a little exploratory data analysis. These are just the points. And I'm going to go in, I'm going to get this model. The model's called Yoshikato. That's the first author there. And I'm going to go into model here and pull up this file. Again, we've got the reference up here. We've got 31 compartments, 40 parameters. And it's just kind of parameters and compartments. And really, we're just turning the crank here and calculating concentrations in the different compartments, and then writing differential equations for all this system of differential equations. But I can, again, I've got this in the model. We don't need to worry about all that complexity here. I'm going to simulate out from the model just a smooth profile just to say like this is where we're sort of baselining where our values are. Again, pitavastatin alone in the green, and then orange is the pitavastatin after cyclosporin. And then I can do the same thing that I did. I'm going to take those simulated data. I'm going to group it by kind of scenario and just calculate that AUC and then normalize it to the first. And so that there's about a 3.6-fold increase in AUC when we give cyclosporin, like just over that first, I think I did 14 hours here. If we give the cyclosporin before the pitavastatin. So if we want to optimize some parameters here, just like the authors did, they did a weighted least squares. They reported that. So I'm going to make a function called WSS, and it's going to take in my observed data, my predicted data, and the weight is just going to default to that observed data. And so we're going to weight by the observations. And again, the important thing here, NARM equals true. So when I've got dosing records or there's any other record in that data set that I don't want to contribute, it's essentially like MDV in non-mem. I'm going to do this the same. We just did this before. We did this before. Same idea. I'm kind of taking a couple shortcuts here. So, but I'll walk you through. So I'm going to get a set of parameters as the first argument. I'm going to name them. I'm going to rely on there's just theta floating around in the global environment. Put a name on them. I'm going to get autolog domain here, update the model object, simulate to generate a prediction, and then I'm going to calculate my weighted least squares. So slightly different formulation, but it's doing all the same things that we did with that endomethacin model and the same things that we did with that even back to the linear model. And that's going to give me the value of the objective function. And again, I want to just return just the value of the objective function. Turn the crank. I'm going to do a little data grooming here. I'm going to optimize this. The authors they optimized on these parameters. So this intrinsic clearance, this IKIU, that's that KI for the interaction between cyclosporin and at the OATP, and then some other parameters that are going to shake out here too. So just generate some initial estimates. They're all in log scale, and again, it's just as easy to do this model as it was the other ones. I'm going to go. There's a package called NLopter that also provides a new UOA method. I've been using that lately, although it seems like it changed a little bit. And I'm going to get these these final estimates, but it's the same thing. I pass in an initial guess function to optimize other stuff that needs to go to that function, and I get a final set of parameters. I get a final objective function value. This kind of, so searching for this xtol rel. This seems like it's something new in NLopter, but I think it gave a positive convergence number. I think if you ran this with the MinQA, oops, I think you'd get it. It would just kind of say you kind of finished in the. It says like normal exit from new UA. So that kind of gives you this normal exit code. The NLopter was kind of complaining about something, and maybe we need to adjust some tolerance on that optimizer or something like that. But this is, I think this gives you the same answer as his new UA, so don't worry about it. But we got our parameters here. Remember, they're on the log scale, but I can still go back just the same way as I did. I can generate a prediction that matches our data set. So now I've taken those final values, I've passed it in that objective function. Now I'm going to call pred equals true. I get a predicted value. And I'm going to do the same thing that I did at the end of that endomethacin vignette, where I'm going to call my kind of prediction function. And I'm going to get my predicted value at the final and the initial value. And then I'm just going to do some data grooming for my observed values, and I can make this plot. Sorry, I think there's just more. Like this is all just ggplotting code here, and I'm just gonna kind of skip over that and just kind of look. So like I like to make these types of plots where I simulate out to say like, this is where the model started, was at the initial estimate on the dotted line. The optimizer moved that prediction over to that solid line. And then these observed values are for pitavastatin alone, the statin on the left, and then the right and the orange is the pitavastatin plus cyclosporine. And then tracking like what that final objective function value is, and then the final estimates. So that kind of turns that same crank, and I hope we've just kind of seen like a lot of repetition there. That was sort of the point behind that. I'm kind of almost getting done to my time here, and I think I got time to run this. So that's estimation in that OATP model. That's the one that Devin's going to take and turn into and do the visualization with. But I want to draw your attention to this another vignette called Tools Optimization Methods RMD. And I'm going to restart my R session here. And this is going to take that same model that we just worked with, and it's going to be a little bit less sort of tutorial when it comes to just the optimization. And I want to do the same thing that we did with a little bit with that the linear model. So I'm going to just run through all these preliminaries, get my data set up, and then I don't think we need the plot. I'm going to load the model, and I want to talk through some of these other optimization methods. I'm going to run this just in case, because if I don't, then okay, there's my pitavastatin and with and without the inhibitor. I don't need this. I need this. So we're going to do, again, weighted least squares. So this should just be the same as we had before. Drew my data, get my initial estimates. Okay. So I want to run this through, and the kind of the net result is in the HTML file there. But this is what we did before. So we did the new UOA. We got the fit. This is the, I think I added this after the fact. There's something else I wanted to talk about there, but I'm out of time. So final objective function values, again, 0.686. And I'll try and remember those values. So let's just go through and just take this same model. So a complicated PBPK model. I've got that weighted least squares objective function, and I'll just see how many different optimizers we can throw at this. So Nelder-Mead optimization through that Optum package, that's the one that comes in the stats. It just comes with R, it comes in the stats package. So 1B this is an alternate Nelder-Mead that I think it might work. That they've just tuned it a little bit different. This comes from that NL-Opter package. I'm going to do this same DE Optum optimization. This is going to take a little bit of time, but again, it's this is that genetic algorithm type thing, and where it's just going to generate. Here I've told this to generate an iter NP. So I'm taking the number of estimated parameters, multiplying it by 10, so it's going to generate populations of, I think, 50 parameters, and it's going to generate predictions for all those different kind of people in the parameters in the population. It's going to pick the one that did the best. It's going to take that to go on to the next iteration. There's going to do this mutation step. And what you can kind of see here, I'm going to back this off a little bit to see this, is that I've only kind of asked for an output. I've only asked for 90 iterations and only output every 10. But you can see that the objective function value went from probably much greater than 2.3, but it goes down to 0.686. And you can see it's kind of a little bit hard to see the parameters evolve, but they're going to evolve as different populations get progressed through these different sets of iterations. And again, because this is a global optimization, I need to say how many iterations to do. It doesn't have any stopping criteria, but I just said take 90, and I'm going to bypass all this data assembly. But I wanted to get to this plot that shows you for each different parameter, we're looking at the best member in that iteration over iteration number. So for the clearance, for the F-bile, Ka, and KTR, and I wanted to show you that we're really searching over like 4 orders of magnitude. So this is a truly, so this is a global search. We could have probably, if we would have over dispersed the initial guesses a little bit even more, we could have maybe searched even greater, but we really searched a huge swath of the parameter space, and that as each iteration goes, it just retains the best member of the population, and then as iterations go along, the population has better and better sets of parameters, and you can see that it's exploring the parameter space early on, and then all of a sudden, especially with the clearance one, where I think there's a lot of information there, the members all kind of start to coalesce around where that final value is going to be, so that by the time we stop those iterations, like every member in the population is very, very, very close to that best member. And so there's a lot less variability of the members in that population, but this shows you a little bit about what that global optimization is doing. And that, sorry, that best member is that orange line. We can do simulated annealing. Again, these global search ones take a little bit more, take a little bit longer time. And let's see, is there something on the end of this? Yeah, I think I'll just walk through the next ones, and because I need to wrap up because I need to pass it off to Devin. So this is hydro PSO. So this is particle swarm optimization. You see this a lot when people doing QSP type modeling. I put the link to the Wikipedia. I've read a little bit about it, and like all I can say is like there's particles and they swarm. So, but it's kind of a cool it's kind of a cool method, and you see a lot of people report it. Somebody out there made a package called Hydro PSO, and it'll do particle swarm optimization. And the idea is that it's like this. I kind of think it's kind of exotic, but again, the same thing is like the same thing with that differential evolution. We've got the same objective function. We pass in some initial estimates. We're doing global optimization. We need to pass in upper and lower. And then we pass stuff through. And so we didn't really need to do any work to tap this kind of this cool optimization algorithm. I'm going to pass this. This takes a little bit longer time to run, but I also included another one from NLOpter called Controlled Random Search. And NLOpter has some really great documentation about what these algorithms actually do or how they work. But I'm just going to pop this open in a web browser. Is that you can kind of, once we get to the end here, I can compare all these methods. So I kind of cache the results from all these different methods. I put them into a table. And this is sort of what we get here, and the kind of what I wanted to get here is that we can get to really to the same answer. So these are the different parameter estimates back on sort of the normal scale. This is where I started the model at. These are where all these different methods ended up at, and you get like basically the same result. And you can do that also with looking at the objective function value. Some of these, like especially like the, well, I guess I kind of let the global search kind of go kind of a pretty wide range. So we were searching a big part of the parameter space, and we made it back to that, made it back to where we really wanted to be, where the fit was good. Like some of these other ones, like Nelder, especially at UUA, a little bit less, they're a little bit more robust to the initial estimates, so that you can start these at quite a ways away from you can start the estimates quite a ways away from where they might finally end up, and you can still make it back and get to that minimum, although there's a limit to how far off the initial estimates can be. But I really wanted to show this, to take this complicated model, and just once you get this pattern down, of just really like thinking about your objective function, like what do you want this to be? I do this just every time I do optimization in R. It always looks something like this. The nice thing about rolling your own like this is that, like, I can intervene here, and a lot of times you do this on when you're calling those global optimization algorithms, where you're searching huge parts of the parameter space, and these parameters kind of generate like bogus predictions, and so you might get NaN or just really wacky stuff. And I can always return like infinity here. So instead of returning the objective function value, I can return infinity, and when that goes back to like DE optim or the simulated annealing algorithm, that just says, oh yeah, those parameters didn't work, and it's sort of guaranteed to just say leave these parameters behind. And you can like also like wrap this and try. You can say, was there an error? And if there was an error, like return infinity and that kind of thing. And so it's really robust when the model's really hard. When you might generate parameters that part of the parameter space that you really just want to reject, it makes it really easy to reject it, because you can always return. You can always kind of check how this simulation went, and then you can return like infinity or just some really high number, and that just makes sure that that set of parameters gets left behind. Okay, that's sort of MRG solve, really quick intro, and then optimization in a nutshell. And if you're interested in getting into optimization, if that's kind of why you signed up today, I would and I was getting started again. I mean, when I do this in companies and we kind of talk them through optimization, we spend like an hour just thinking through this linear example and figuring out what happened here and how to set this up and really get these mechanics down about how that optimization is happening. Don't go straight to your complicated PBPK model. Spend at least a little bit of time here to say, yeah, I get comfortable with this workflow, and then make it a little bit harder. Whenever I start an optimization, like it's, I put this local sensitivity analysis thing in here to say like, I almost do some kind of sensitivity analysis, and just to say like, this is for the, this is for the Statin model. So you can just plot, this is sort of like this local sensitivity analysis, the sensitivity coefficient versus time, and just ask yourself, do I have information in the data? I mean, hopefully you're doing that all the time, but I think especially when you're doing PBPK or like QSP, you've got these over-parameterized models, like spend some time really honing in on like, what can I really estimate? Where's the information in this data? So I've got the KA is in the pink here. Well, that kind of makes sense, right? PK is influential. The KA is influential up at the beginning of the profile. Obviously, the clearance is influential sort of way out here. I picked the volume of the adipose tissue in this yellow line as sort of like a negative control, and that's sort of like non-influential on any part of the profile. And so I took the time to do this local sensitivity analysis and say like, well, let's make sure we don't try and optimize the volume of the adipose tissue here. And just make sure that there's information there in your data. So take the time to do that. And then like the next step is I would just optimize like a single, like one or two parameters, like do ones that are obviously going to be influential, like KA and clearance. Get those estimates down, and then kind of step in and making it a little bit more and more complicated as you go. So that trick here is really to build up in complexity, take time to assemble your data, and that's how it gets started. So, okay, so that's my deal. We can do like maybe one last round of questions here, and I can take that, and maybe we can even just, well, we can take one round of questions. If you need to go break, you can go break, but we'll do questions, break, and then Devin's going to pick up with this same model and then go into the visualization.
And to to kind of, before we get into the questions, in case people are breaking, to kind of set the tone, if you're kind of wondering, what's coming in the next kind of 2 hours, and if it fits your proclivities. So we're going to take this model, but actually the really we're going to only spend about 5 to 10 minutes just to frame a problem that we want to show with Shiny, in particular, giving a non-technical decision maker the ability to kind of play with those parameters themselves in kind of a graphical interface. But the majority of the time actually is going to be spent really talking about the areas of being effective with Shiny, kind of into the production. And like, when by production, I mean like giving it to other people that are not yourself. Like how do you be successful there? How can you make it so that you can mirror or work with local development? How can you think about scenarios like when a user comes in and says, I was using your app and it broke, like what do you do? So we're going to kind of actually start to break apart some of the concepts that kind of don't get captured in conferences or books or other pieces, and kind of go through some of the experiences we have, some of the tools at your disposal, and use that as a lens. So just wanted to set that out as people might walk away. And what I'll do is I'll say that we can kind of keep it open for questions or otherwise till maybe 1:15, and then we'll kind of slowly ramp in case people need a little bit more time even beyond that. Okay, so again, I'm going to fly through this. Usually in a day or two workshop, we go through this slowly and really talk about it. But the intent here is, if you are not familiar with these concepts, I'm not looking for you to fully digest them. I'm looking more for you to pick up some vocabulary and some nomenclature around what I'm going to be kind of moving through, with the majority of the time we'll spend on live code. As well as, maybe even for some people, crystallize some concepts that they've kind of intuitively been using, but not had something kind of formal behind. So the idea with a Shiny app is that there are kind of two core components. There is a server and a UI. Right? The server side of things is where all of the R computation is being done. It's where the processing occurs. The UI is about displaying whatever the server is calculating to the users, so that they have some meaningful information that they can kind of take out of that. The server and the UI can interact back and forth, and they're going to interact through this bridge called these outputs and these inputs. And I'm going to kind of show you how that fits together. But before we kind of hit on the concept of it, it kind of makes sense to even connect what this even looks like as a shell of code, right? So the idea is, if you want to run a Shiny app, like this is the simplest Shiny app that you can ever imagine. You call Shiny, you define a server. This server is going to take an input and an output object, and then you define a UI. One of the key things about the UI is that the UI itself is really about just constructing a bunch of HTML, and also understanding what JavaScript and CSS, the thing that give a web page its interactivity and its look, need to pass along to the user. So there's not really any like logic that goes on in the UI itself. You might use logic to build up a specific design in the UI, but this really, if you can run any of the pieces and bits and bobs of the UI code, and literally what you're going to get back is you're just going to get back HTML. And this is the kind of one of the brilliant pieces of Shiny, is it has completely abstracted the need to understand those languages. And so you can immediately start developing applications with just using this kind of widgetized framework, where you can focus on the server logic, which is where your business logic is going to be going down, where you're going to be able to take a lot of the things that you normally do in an analysis and start to present those in interactive ways. So the way that this interaction kind of goes between the server and the UI is this: think of this input and output pipe that's going to be sending kind of messages back and forth. And we need some way of being able to connect which messages are meant for what. So, some computation happens on the server. It's relevant to some output that's ultimately going to be displayed to the user. And so the way that these things connect together is there are kind of two core types of functions that you're going to use inside the server and the UI to kind of map those things. So the first thing is that we want to be kind of describing is we want to take what things we ultimately want to show the user, and the kind of the concept used even in all other kind of programming languages that involve interfaces is usually the ultimate act of kind of presenting to a user is often called rendering. So you're going to render something that the user can see. And this is what Shiny gives you. So they have a bunch of pre-baked render elements. So you have render table, render plot, render data table, et cetera, et cetera. So these are all things, the render objects are going to happen on the server. On the UI, you have a sibling kind of thing that still uses the core object type, but then rather than it being a render, it's instead an output, right? So you render something and then you output it onto the UI. So table output, plot output, data table output. So if you kind of take away one thing and one place that, you know, even when I'm coding quickly in the Shiny apps, I absolutely mix up sometimes. It's just like, which one goes where? The render components go in the server. The output components go in the UI. If you mix them up and you start trying to put a table output in the server, Shiny gets all confused. And so just kind of keeping these things mapped is going to make you kind of successful for thinking about how you need to ultimately map your computations to things that the users want to see. So there's a view function built into RStudio, right? You can type in view your data, and then boom, you have this nice kind of data table that's gonna show up. And you know, if you thought about building that identical thing in Shiny, if you will, right? The idea is if you had an object, a data frame, a data set that you wanted to show, you would be putting that in the render table, and you need to give it some name, right? So the idea here is this render table, we want to send this through the output to the user, and we're going to call it T_theof. I like to namespace my outputs. So like T_ for tables, P_ for plots. And so this helps me kind of scan my outputs quickly for what kind of ultimately they're going to get connect to. And then on the UI side, we're going to map whatever the output name is to what this is going to be on the UI. So in this case, likewise, T_theof, and it's just a string. So if we wanted to do more than just a table and wanted to also put a plot, again, there's no interactivity yet, just showing how Shiny can start to lay out things. This is where you can say, in this case, we're going to have a table and a plot. So if we look through here, and again, I know I'm going real quickly, but these, you know, you'll have these slides, and hopefully these things can kind of connect together reasonably here. So we have a render in the server, and then we have an output in the UI, and we connect them by name. Likewise, we do the same thing for plotting. We're going to connect them again by name. A couple things to take away from this, a couple subtle elements, is the first thing is that this is absolutely currently a completely runnable Shiny app. And in fact, if I run this right now, this is what the app that I'm going to get back looks like as soon as you click run in RStudio. So what this allows is, without having any degree of reactivity, you can actually start building interfaces. Oops, excuse me. You can start building interfaces to kind of mock up what ultimately you might want to turn into reactivity way early on. So one technique you can use as you start to dabble in Shiny is to not even make it reactive, not make it intelligent about responding to changes for the user, and just saying, like, where do I want to put stuff, right? I want a plot here. I want a table here. You can just use regular old code, connect them with these render things, and you can show what those outputs might look. And this is one way to start kind of getting consensus early on from other stakeholders around what an application might look like or need to do. The other piece that this kind of starts to hint at a little bit, but is probably one of the first mind-bending elements of Shiny that that people kind of can take time to wrap their heads around, is that notice like my render table and render plot are not identical to how my UI is laid out, right? First, I have the render table and then the render plot, but I switch these things up and I have the plot first and then the table. And in fact, the ordering inside this server function has no bearing on anything to do with how things are laid out in the UI. And so there's many things in the kind of server object that you do not need to maintain some degree of order around. And this is something that definitely kind of throws people for a loop where they're used to kind of writing code that progresses linearly. However, with Shiny, it doesn't have that kind of construct, because in reality, what is really happening is when the server boots up and it's kind of collecting these expressions, right? This is the code you need to run to present a plot. This code does not actually get executed until the application has actually been running and started already collecting information or setting information. And so because of that, because it actually kind of runs later than where it's defined, a number of those kind of pieces that feel like they need to be linear actually don't, because of when they actually get executed. It's in the same vein that you can kind of like define a function, in one place and then invoke it in a way later place. The kind of same thing holds with Shiny. The invocations do not exactly happen where the original code itself is run. So a couple very quick gotchas, or actually just one gotcha really, that I think is the next thing that people will kind of commonly stumble upon. There's kind of two things right here with this plot. The first thing is that in this UI, I have the same plot output twice, right? Saying I want to show this figure twice. Now, for this particular application, that might seem kind of silly. Like, why would you have two plots, the same plot side by side? But what happens with kind of more complex applications that you have like pages that you can navigate to, frequently you'll get to a point where you're like, I want to show this thing in multiple places so people can kind of compare it against different other elements of the application. With Shiny, you cannot do this. You can only have one output. If you run this, it will complain and blow up. Now, there is a more subtle thing that can also happen. If you notice here, I also have this misspelled, right? Con time, not conc time. Of all of kind of Shiny's pain points, I would say one of the biggest pain points for diagnosis is the fact that Shiny does not handle misspellings well, because it's not intelligent enough to know, oh, you actually meant conc time, right? Because you can dynamically generate output names, especially in looping functions or otherwise. Like, this is a completely valid name that could arise. Like, you could have that name generated dynamically, and so Shiny is going to happily accept that. But then, of course, because it's not actually connected to this conc time object, it's not going to show anything. So people will be like working. They're going to add some new inputs, and then they're going to be like, why is this not showing up? So my piece of early diagnostic advice to you is, if you have an app that the code is running, but something is not showing up that should be, the first place you should always look is, are your names correct? And that will save you many, many hours of debugging. So I'm going to exit the slide deck for a second, because I actually cannot see the chat while I have the slide full screen, and just see to make sure I haven't completely like lost half the people already.
I think we're good.
Cool. All right, there we go. All right, so then I will plow back into the full screen. Keep on rolling. Okay, so we just talked about the outputs, right? How to get a thing onto a page, but frankly, that's something that, especially with the advent of things like R Markdown, people are being able to do that in more and more sophisticated ways that don't have any degree of interactivity and can still bring a lot of kind of value to the organization. And so the major differentiator that, of course, Shiny brings to the table is the fact that not only can you present outputs however you so choose, you can also start to collect information from users, decide how you want that to be computed, and then present them dynamic outputs. This happens in a similar way that we have those render functions. We likewise have those, and then the appropriate outputs. We also have inputs, and these inputs are going to be defined in the UI side of things. So these inputs will collect some information that's going to help build up a particular type of input widget. And there's a broad landscape of widgets at this point. There's a number kind of baked into Shiny, right? Drop downs and sliders and calendars and input boxes and check boxes and checkbox groups. But one of the really exciting things in my mind in the last couple years, and especially in this last year, has been this amazing kind of flourishing of kind of UI frameworks and other widgets that sit on top of Shiny that not only can kind of start to take your apps to the next level with respect to, like, it doesn't always look exactly like the kind of same type of vanilla bootstrap driven app, but rather has a nicer look and feel, which is cool. But it also actually, some of these widgets have much more sophisticated things going on. So you can actually make your applications truly more powerful, not just kind of look nicer. And so, you know, if you are developing Shiny or you have developed Shiny in the past, definitely worth tuning in to kind of the developments ongoing, both coming out of RStudio directly, as well as the kind of broader ecosystem. So in the same way that those render functions connect to outputs, right? Like we have this render table that is named table 1, and then it's going to connect to this table output called table 1. Like the logic basically is completely inverted for the UIs. So the idea is in the UI, you're going to almost always define a an input ID. And so in this case, we could have a slider that we're going to call num rows for the number of rows we want to kind of show in the table. And then you can see in the output that we're referring to this value as input $num rows. And so this is the dynamic value represented by the slider. So as we slide it, input $num rows changes. That change triggers the table re-rendering, which then passes along the new table such that the user sees that change. So to kind of connect those together, we have the num rows connecting. Likewise, we have the table connecting. And this is really like the secret sauce of Shiny. The thing that differentiates it is the elegance of the coupling between those inputs and the outputs in what's called a reactive framework. And so if you've never heard of reactive frameworks, you know, this in and of itself is a fascinating kind of deep dive topic worth discussing. But in short, one of the big things that Shiny brings to the table that normally is a huge lift for application developers kind of in traditional frameworks is being able to identify what the heck actually needs to be run. When something changes, what needs to be rerun. And ultimately, as stuff is rerun, how does that also need to propagate back to the user? This is a place where all of that logic can be like multiple full-time people working on building a traditional app to just handle those components. And Shiny kind of gives you that for free. Now, like anything, the grass is kind of green and can always look greener before you kind of walk in. And so there are absolutely rough edges around some of the byproducts of what that tight coupling kind of can force you to do in certain situations, especially when you're trying to scale applications to like many users working on an application at the same time. But by and large, this framework is simple, elegant, and very, very powerful. Kind of from my own experience as someone who kind of like started with Shiny, then spent a lot of time learning about kind of traditional application development, now coming kind of back to Shiny. It's one of those things that sometimes you might sit there and wonder like, man, is this not like a real application or what do real programmers use or something? The fact is that that Shiny in and of itself is an enormously powerful framework that allows you to, again, not have to think about a lot of the day-to-day things that people have to invent over and over and over again. And so this is all to say, if you are interacting with your IT group or you're interacting with some programming group that builds traditional applications, don't let them stomp all over you if they're like, oh, R, Shiny, that's not like real application development. No, you got to do it this other way. That's absolutely positively not true. And if anybody ever tries to stomp on you and say that, you give me a call and I'll make sure that they get their their minds straight about that. But this reason that I just brought up kind of dovetails into where I want to talk about for the remainder, for the vast remainder of this kind of hour and a half that we have together, which is that because Shiny can give you so much so easily, one thing it can do is it can unlock capabilities for people that are not aware of those rough edges, or those places where you can shoot yourself in the foot or otherwise. And so there can sometimes be this kind of very hyper positive initial experience that then comes like crashing down when it gets into like what we'll call production usage. And again, for right now, what I'm going to define as production usage is something running somewhere where you're not constantly hovering over it, right? Where you're like not launching it from your laptop. And if something goes wrong, you fiddle a little bit with it and you relaunch the app. It's running in a place where people are consuming it. No one's necessarily looking at it at all times. From a simplistic perspective, if we consider that, this is the area that I want to talk about, because in my mind, it's not actually that hard to level yourself up to do a lot of the things that differentiate an application that's not following a lot of those best practices versus following them. The key is you need to start with those best practices from day one. Because if you try to roll those in after you already have an application kind of built up, it becomes kind of a nightmare of unraveling the spaghetti of code that has been mixed and mangled together. And so what I want to do is I want to kind of go through this kind of staged process of how I like to kind of scope and build an application, a very simple one, right? Given the time, but how we can approach that mentally from kind of inception all the way through an initial implementation at this point in time. And hopefully we now have this kind of vocabulary around what's Shiny doing with the inputs and outputs that I'll kind of, throw in some more bits and bobs of information as we go. So let me pull over our studio window. All right. So I have some of this stuff kind of already there. It's it's very much not worth spending time with me kind of typing it live, and you watching how quickly I can type on the keyboard. But I think there is something to be said about kind of watching code evolve naturally. So I've kind of like half prepared some of this stuff that we can kind of clean up a little bit, but we don't have to type everything out. But in order to talk about designing our Shiny app, this is where I would like you all to start kind of going forward. I want the mental model of how to approach building Shiny apps to actually start with an R Markdown document. Clear everything out from my session real quick, and we're going to start things up. The reason to start from an R Markdown document is Shiny intrinsically has a longer development kind of cadence cycle around what it needs to do, right? Like every single time you click run app, it has to boot the app up. It has to kind of source any of the stuff that it needs to run globally. Maybe you have to load data in, maybe you have to do other things. And then it's gonna have to like render all of the widgets and display them, and you're gonna get your kind of web browser popped up, right? It only takes a couple seconds each time, but for the most part. But each time you do it, it's going to take those couple seconds. And so what we want to shortcut is early on in that kind of scoping cycle. We actually, to me, to most effectively design a Shiny app, you should actually be designing what you want the Shiny app to do outside of the contexts of Shiny completely. And so this allows us to iterate quickly and think about what the app is going to look like. And so the way that I like to do this is I like to take an R Markdown document and kind of like split it into some chunks, right? The first thing that you might have is you're going to have, and when I say chunks, I mean like document chunks, not like code chunks. So what we're going to have is we're going to start with setup, right? So this is where anything that you want to run, kind of like when the application were to start, this is a good place to put in setup. So this is going to mean loading libraries. In the case of our MRGSolve model, kind of sourcing it in to kind of compile it so people don't have to compile it themselves each time. So that's kind of like the first piece. The next piece is we might define some constants, and I'm going to use this term again kind of lightly. Like these are pieces that that might be easier for you to actually store as an object, or you might need to store them as an object, but for the moment they're kind of fixed. These things eventually might evolve in the kind of course of us building up this kind of application framework into things that will become reactive or inputs one day. But the point is that we're starting to collect all of the stuff that ultimately is needed. And so this is a place that we can kind of look at easily. Then we're going to have our computational logic. Some people can also call this often the business logic. And this is where whatever the thing that you're trying to do, you're going to try to capture it here. By doing this first in an R Markdown document, the other thing this kind of forces you to do is it forces you to kind of confront this business logic early and think about some of the design, if you will. In particular, one of the things that we want to avoid as much as possible is putting logic kind of deeply nestled within the Shiny application, like render functions, right? The idea of anytime you have to make a change, you have to go through this staged approach of fiddling with the application itself, making a bunch of tweaks, only to get to like finally the place that you're making code changes around the business logic, right? The computations you need or otherwise. Like that is a development time sink. I've seen a lot of people that when they get stuck with an app like that, they have to go through some song and dance every single time they make a change of like launch the app, like upload a CSV file to the app, click, 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 click. And then like they finally get to the thing that they're working on, showing a plot differently or giving some conditional logic somewhere. This allows us to start breaking out our computational logic in a way that is digestible, and you can think about how you're ultimately going to shift this into the Shiny app. And then the final piece is the outputs. The outputs should represent the things that you want your users to be able to actually see, right? And those are things that ultimately, like, hint, hint, will make to a render function. And kind of coming back to the statement that I just made is the idea is like these outputs should be as absolutely dumb as possible with respect to if you are sticking computations here, then you need to shift the computations upwards into the kind of computation section. And then the outputs should really just be about, in our case, essentially printing them. So for example, an output like this of actually putting the code that was used to do this summary calculation. I'll come to what this code is actually doing in a second. The idea is like, this is an anti-pattern. Again, the reason behind this is not only does it force you to have to kind of start dealing with shiny and like where things are going to render and doing computations in those render elements where you shouldn't be, but also you can quickly get into situations where like this, where you have this summary calculation where it's a table, you actually need the summary calculations again in a subsequent plot. Well, that means that unless you've already stored this somewhere, are you going to take this exact computation and copy and paste it in there? No, that's not, you don't want to be duplicating calculations. You want to do it once and then use it multiple times. And so this is going to force you to kind of start to break your logic into these chunks. The final kind of statement around this before I kind of get off my soapbox and talk about this code itself is the other benefit that our markdowns can kind of give you is they're more easy to share with other stakeholders. So when you run into a situation of like you've developed in our markdown document, you actually want to share it with someone who is reasonably technical or otherwise. They don't have to necessarily know shiny at that point in time, right? They can just be given in our markdown document and say, look, this is what I'm trying to do with this document, right? I have these outputs that I'm calculating. So they can kind of almost work their way back from if you were trying to do these things, right? These are the things you're trying to present. How did you get there? You can have these dialogues. You can share these around in emails a little bit more easily. And in fact, one pattern that we've been using more and more is to share these as kind of like drafts of what the ultimate outputs might look like through like RStudio Connect, like publish them as a static doc, right? No interactivity yet, but just being able to say, hey, are these all the outputs you expect? This often will cause people to kind of be confronted with their kind of mental model of what they were thinking an application might do and might present and go, that's not exactly the plot that I was thinking. Or, oh, now that I see this, could you also have one more table or one more plot or something like that? So it allows you to kind of open up that discourse where they have something very rapidly to kind of touch and feel and play with and think about before you've had to do too much work kind of navigating the shiny reactivity jungle. So let's look at what we're actually going to do here. The kind of simple case study concept that we'll talk about, and we can run with this in a bunch of different directions kind of dynamically, is the model that Kyle was showing you, the Yoshikado model, allows us to explore kind of the drug-drug interactions, especially with cyclosporine on these statins. And we kind of talked about this, I think, early on, but just to kind of, again, like kind of level set around the concern is that as they start to mediate like OATP transporters or other kind of DDIs that isn't necessarily cyclosporins, but something that might mediate, for example, CYP metabolism, where statins are kind of sitting in the liver, there can be concern around a drug interaction that may or may not put people at some sort of risk. And so one thing that modeling is often used for is kind of exploring that space of what can we do to mitigate risk in some direction, or how can we make development decisions in our pipeline. And so in this case, the concept that we're going to go with is imagine we have this PBPK model. It's developed from literature. It's built around the parameters for cyclosporine. And we have a new moiety, a new compound that kind of has similar characteristics and but isn't the same. And the idea here is to kind of explore and say, how might this compound play out? And maybe, in fact, we have multiple kind of versions of this that have slightly different physiochemical structures or some other thing that could change some of the parameters in a way that we could actually explore the impact. And we wanted to kind of take it one step further beyond just exploring, like, what if we change the kind of mean value, the typical value, and instead say, what if we also want to bake in kind of using a pseudo Bayesian framework and say, like, what if we want to also explore the uncertainty around things? So we want to define, for example, and say, what is our likelihood of some adverse situation occurring, or in our case, we're going to make up a scenario and say somehow your clinical colleagues have been able to identify that a daily exposure, so a partial AUC over the course of one day of greater than 200 is bad. It's something that we don't want. It's something that we want to avoid if at all possible. And the question that has kind of come back to you is there's a couple different potential compounds, maybe a couple different manufacturing processes or other ways that we can change the overall compound itself to kind of behave differently. And so we want to add some adjuvants or something there to make it behave differently. Like, what should we do? How can we make a decision and help us like put some degree of quantitative information behind these kind of questions that are arising? And so what this code here is doing is we're kind of setting up where we're saying, okay, we've gotten the two drugs that we're giving. We're giving a single dose, and we're going to do this for 500 individuals. And the idea is right now to kind of zoom the lens in, we want to just look at one parameter. And so if you kind of vaguely remember back to what Kyle was showing at the end, one of those parameters, IKIU for inhibition, was there. And it definitely was sensitive over most of the time course. And so given that there is some sensitivity to this parameter, then there's some degree of likelihood that changes to this parameter might change some of our outcomes. And so that's what we want to explore a little bit. And so the structure that we're constructing here is basically to say, well, what if I take and create a bunch of individuals, if you will? Let me make sure I have my models all loaded, my constants defined. And then now we're getting into this iData, right? So the iData object in MRGSolve allows you to change a parameter for an individual, right? So we're kind of using that concept of an individual to define each kind of simulation scenario. In particular, ones where we're changing this IKIU. So what we're doing here is we're saying, give us a log normally distributed situation where we're going to have 500 draws, and we're going to use the existing value. So we're pulling that value out of the model. And we're going to use about 30% coefficient of variation, or 0.09 is the standard deviation. So this is the RL norm is just built into R, I believe. Check real quick. Just extra RL norm. Yeah, so it's just built right into the stats package. And you can see here with RL norm that they want to not just get the mean, but the log of the mean and the standard deviation log. And so what this is going to do is it's going to generate a bunch of kind of values that we can then feed in to MRG Sim. And what we're going to get out of there is a bunch of daily AUCs, daily exposures, right? And so the idea that I had said is, again, imagine we had this situation where 200 was established as a threshold for concern. And so the question then kind of becomes, given this parameter was kind of within that distribution, like what type of risk are we looking at here? And what we can see is that from this, the proportion above the threshold is 0.078. So about 8% of the scenarios resulted in an AUC over 200. And then we can also see the kind of average of 158. Now, what we can do here is we can start to change things, right? And again, we're not yet in building Shiny app mode. We're just in a dialogue around like, what do we have to offer that this model could allow us to explore? For example, what if we were to change this to only be 20%, right? We were able to go do another in vitro study that would give us more confidence around the precision of the parameter estimate that we were going to be using, that this was actually representative of the true value. That additional data would help collapse some of that uncertainty. Now, how confident would we be at that point in time? What's the risk? If we kind of rerun this, we now actually see that that drops by changing some of that uncertainty from 0.8 to 0.02. But of course, the average stays virtually identical. And we can also do things, of course, like plot this. So the scenario that we can imagine is, you sit down with your laptop, you start discussing this, especially with some, less technical person, and they say, this is amazing. Like, I would love to run out some scenarios myself. How could I do that? And you, of course, go, I have been jonesing to build a Shiny app. Let's build you one, deploy you one, and allow you to start to play with this. Now, again, we're just talking about one parameter. If we actually look at the model itself, in this case, we can see that this model has like 43 parameters. And so you can imagine wanting to tune many more than just this one. But this is a kind of a framework for at least the dialogue around the Shiny app piece. So what we want to do is we want to take this and we want to transform this logic that I've been doing right now, which is like going in and just manually adjusting parameters, right? Like, oh, what if it has more uncertainty around it, right? Let's crank this up to 0.4. I run this again. I get the summary calcs, and I just like, let's just look at this visualization. And now we can see that we've moved up to almost 30% above that kind of threshold of 200. So by not changing the parameter value itself, by just saying we're more uncertain about it, it all of a sudden can help characterize that maybe some of the assumptions that we're making around this model may not be something that we can be completely confident about given the information at hand. Maybe it's worth going and collecting more information to improve precision, for example. So we have this. Now let's think about what are some of the changes we might make to this application in order to kind of shinify it. Well, the first thing that we would want to do is we're going to say, well, anything where my answer would be like to run it once, to look at it, and then to like go change some value and run it again, like that won't work, right? We need to turn these things into values that can ultimately be bound to inputs that we can kind of change dynamically. So for example, here, I'm going to say, well, this is a value So we're going to say IK, IU, SD, or this is actually CV. We're going to take this, and this we're going to turn into one of our constants. Right, so we're going to start growing this thing out such that the code inside this business logic is something that by the time we're ready to transition this into a Shiny app that would actually be running, is something that we really don't have to do much changing wise. If we look here, one of the other things that we might want to do is not just change the uncertainty around the parameter itself, but also change the value of the parameter. And so one way that we could tackle this is, of course, to like directly like pull this out and then just try to kind of replace it. But one other thing that we could do in order to kind of discuss it from the lens of like maybe some change from the known value is we could also put some like scaling factor, IKIU, scaling factor, IKIU, scaling factor. And by default, we'll set it to 1, right? So the idea is by default, when we run this, it's the value as per given by the model. So when we run this now, I'm going to get the exact same code, the exact same outputs. However, I'm starting to make this such that I have more control over how these inputs these potential inputs, I should say, get defined. And so to grab a couple more things, right? This is also something that some threshold, maybe it's 200, but maybe that's something that you want to have a discussion about. You know, what if it was 250 or 190? So we'll define dynamically that threshold. And you know, you could continue to roll out these types of these things that can be variableized. And so, but this gives us plenty of ammunition to kind of now think about what we want to do to stick this into a Shiny app. So before I get to, actually, nope, sorry. There's one more thing. Is so the other piece that was super valuable for us to showcase in a lot of these scenarios is actually not just changing the value on the fly, right? So even if we were able to say, like, let's define this threshold now as, you know, 180 and just go and kind of like rerun all of the chunks below it, and now I can see the difference. Like, the fact is as human beings, we're very visual people mostly, and we're very astute at being able to differentiate changes. However, making that change and kind of looking at a new static figure, being able to tell what did exactly change can be hard. And so whenever I'm building Shiny apps where the intent is to allow someone to explore, one of the things that I always like to do is make it such that they can always see what that reference scenario or that reference case looks like compared to what they are actually playing with themselves. So we want to grow this code base up a little bit such that not only can we show the one scenario that we're discussing, but we want to show this scenario compared to that reference. And so this means now doing a little additional refactoring around our code such that we can kind of be able to do some of that overlaying comparisons. So by the way, I just got a message from the chat. So this code that I'm playing with is not in the PKPD content. I will admit I was still fiddling with this while Kyle was speaking, and so I will get this out to people at the kind of in an hour. I will push this out, and we'll also have the link. So it'll magically appear in your home directory as soon as kind of we get off the call, as well as we'll have a link for people to be able to kind of explore this code base itself. Okay, so what we want to do is we want to take this and change this from like that kind of single situation that we're kind of running over and over again to a reference situation that then we can also have a comparator situation. And so what I'm going to do here is I'm going to take this, and this actually really represents the comparator situation, right? Like I've added a scaling factor, I've added this variable. And so I'm going to take this and I'm actually going to rename this like comparator. And we're just going to start doing some renaming. And so we're going to say the output of the comparator. We're going to say iData comparator. And this is starting to look, this should also run again, okay? By doing this in our Markdown document, again, I don't have to be like changing this code and saying, I hope this runs. I hope I didn't accidentally miss some, naming piece. I can just be running this again quickly and rapidly and iterating on this code base without it being, again, nested inside some Shiny app somewhere. So I have my comparator. I'm going to be calculating things. The other thing, whenever I think about now moving from that like lens of I'm thinking about one situation, one scenario, one something, to I may have multiple, by the time you get to tabulating or visualizing that, you're going to need some reference label to be able to know what data came from where. And so the other piece that we need to then add is some extra column that's going to tell us what this is. And so we'll say that the type is comparator. I hope I'm actually spelling that right. So now we have virtually the same situation, but we have now this extra type. And so this still can hold the same a little bit. For the moment, we're going to have to keep changing this though. So now we have the comparator. And the reference situation is where, again, this kind of like breakdown of like where it makes sense to put stuff becomes super important. So in one lens, you might want to keep this in the computational / business logic, right? The stuff that would need to get calculated, potentially over and over again. But the whole thing is that from a reference scenario, you're defining it once and saying this is the reference, or at least that's the assumption we're going to make, right? You might actually want to make a dynamic reference scenario. But when we have that reference scenario that only really needs to be used once, to me, the place to actually move this is into the setup, right? There's no reason for the user to have to calculate this live in their session. We should only need to calculate it once and then just reference that value over and over and over again. So what I'm going to do is I'm going to actually move this whole thing up into not this place with the constants, but rather above this into the setup area. And I'm going to change all of the references to comparator to reference. So we'll just like grab all of this and say change comparator to reference. And so now we have all these reference things. Now this code won't run yet because we have things actually defined in the constants that we're using. And so this brings us kind of rapidly through this evolution towards now we have to kind of start to face the music a little bit of what things could be truly constant versus what things do we want to let the user be variable, but we're going to kind of hold fixed. Because again, this is kind of like, I really shouldn't say this is constants, these are inputs. So what are things that ultimately we want to be inputs? If we want the user to be contributing to them as an input, we obviously cannot have that value during setup. And so you can make a decision of, do we think this is something we want the user to be able to play around with? Or is it something that, no, we're going to make this a fixed situation? And so maybe I'll just make something up and say, you know what, the number of reps we're going to hold fixed. So I'm going to actually promote this up to the setup area. Likewise, maybe for now, just given the complexity or the simplicity of the app, I'll even move the drug dosing. And this might be something we eventually want to move back into the user land. But for now, we'll just specify this for simplicity and time as saying, hey, let's define this in the setup only. And then we can reference it, because this is kind of the meat of where the user stuff is going to go on. So I'm shifting stuff around. And then I can try to run it. Now, if I run this code right now, it will run. Prove it. But there's a bug in this code still. It's a bug, you know, again, I'm kind of moving fast, but this is a scenario that people will often run into, right? I've been shifting things around and, you know, pulling things from down below and pulling this up here. And in this case, the bug is that I have a couple of these inputs here that are actually being defined in the setup area right now. And so when this actually came to kind of running it in the Shiny app or end to end, it would fail. So this brings me to my next kind of tidbit tip. And that is, if you are doing something that does not require an enormous amount of kind of like computation, right, where it's just a couple seconds to kind of run through things, it's not a bad practice to occasionally, in my mind, clear your session if you find yourself having to kind of like either be shuffling around and refactoring where your code lives within an ARM Markdown document, or the other scenario that people frequently run into where they get bitten is if you have multiple ARM Markdown documents side by side, where you might define a variable in one, start referencing it in the other, but since it's kind of like in your global environment, you're running it and you're like, this all runs fine. And then you go to knit it and it just goes kaboom. So we can kind of get out in front of that a little bit and say, every once in a while, after doing some shuffling around, I might restart my session and see what happens if I run end to end. And in this case, it should hopefully explode, which it does. And it says, you haven't defined that. And I go, of course. And so in this case, I could then go in here and decide how I might want to handle these. I personally like to absolutely minimize the place where I just have numbers with kind of no context. So for example, going in here and just doing 0.09, if that was our reference. To me, as a mechanism of code communication, you should always strive towards people being able to read pieces of your code and being able to like digest and be like, I understand kind of like what you're trying to get out here. And so in this case, I would much rather have these things be defined here and, you know, add something to this. Say, for example, going in and we'll add some like reference here. And so we can now define these as the reference values. This is clearly communicating what the heck this value is represented by. Now we don't need actually a scaling factor because there's, you know, we're not scaling it yet. So we can just get rid of that one. This one we can grab in here, throw it. And then the threshold reference is something that we also need for calculating the summary, which we have not done yet. So we need to now do one last thing, which is we have this kind of threshold and these other pieces defined. We run this and we think about what we actually have, what we're doing here, and we can see and kind of come down here and say like, well, we are going to need this summary calculation for it. And so we need to grab a little bit more code. And this kind of is a place where you have to make judgment calls around the trade-off between code duplication and computational efficiency, right? If we were to say, keep the raw values of the reference here and use this directly each time. For example, what we would need to do here is we need to, in order to calculate this, we need to actually bind these guys together, right? So like bind rows, and we're going to bind both the out comparator and then the out reference. And we're going to group by the type. The nice thing is this calculation only happens once, which is great for like the whole don't repeat yourself. You have code in only one place. The downside is that it means that you are actually going to recalculate this proportion above threshold in this 50th quantile over and over and over again. And it is an absolute gray area with respect to what is better or worse. I will argue that in general, electrons are very cheap. Human errors, such as duplicate code that ends up drifting, where you think they're the same, but you make one change one place and forget to change it in the other place to do the same thing, are very hard to quality control, very hard to diagnose. And so my preference is to absolutely try to minimize the duplication as much as possible. And if you get to a point in time where redriving certain things does actually start to provide kind of negative user experience, the inability to scale to the number of users you want to be able to, for example, concurrently use your application, then and only then do you start to say, hey, is it worth duplicating code in some places so we can do some more sophisticated like pre-calculations or caching or other things where we have to do less work, therefore we can be faster. And so, so in this case, I don't need to, I'm making a decision not to calculate the summary information here. Rather, I'm going to recalculate the summary information over and over and over again in combination with the kind of dynamically generated comparator data. But I'm willing to take that trade-off because of the fact that it keeps my code a little bit simpler to reason about. So let's actually source these guys. Move this back to 200. That runs. This should run. And now our summary calculations, we have the proportion above threshold, the Q50, and our comparator and reference. So we have our summary calculation still. Now we need to do one last piece, which is this plot, right? So instead of having just the output, we now have two outputs. So we're going to grab the output comparator. And we have the out reference. And we need to give them some coloring. And so for many of you that have companies and company color palettes, you get what you get what you get. However, if you have some freedom and flexibility around the colors to decide, one nifty little thing that ggplot allows you to do is you don't have to just use like declarative color codes like black or blue or green. Instead, you can actually use like hex codes. And so what I have done in the past is kind of collected some myself, but to kind of show you how easy it is, you can just search for things like color palettes, find a color palette that you like the colors with, and grab these hex codes ggplot understands. And so what I'm going to do is I'm going to grab 2 of these just to show what that looks like. So in this case, we'll take the reference and we'll make it one of these numbers. And then we'll make another one, different color, ED553B. If you are in a company situation, one thing that you can do is go ask for your company color schemes, where you can actually hopefully get the company hex codes associated with whatever kind of design scheme that they're using. And so you can start to use your true company colors directly, even in your visualizations. And the piece that I always mess up with histograms is it's not color, it is fill. And so we can kind of see where these things are overlapping. We can give some shape to the histogram by actually going back and setting that black color. And now we can kind of see these things are pretty much overlaid on one another, right? And that makes sense because they're actually like the same values. So other than the seed of what we were simulating, they should be identical. But what we can now do is we can go in and say like, well, let's change this again to go from 0.9 to 0.4. So this no scaling factor, no anything. We go and rerun this. And we're going to see what the differences look like. So now that comparator turns up to 23%, and you can start to see the difference here, and that comparator is going to start to spread out, right? Because there's kind of more there's more uncertainty, and so it's a wider distribution. So the next step might be, continuing to even refine these outputs, right? Get a legend on here, get a couple other pieces together. But at this point in time, in my mind, we're kind of like getting to a point at which you should feel reasonably comfortable around being able to be like, I have a set of code and logic that I could start to translate into a Shiny app. This could be shared around. I have my things kind of decoupled enough, and I can think about the kind of various places this might live in. And so before I kind of go to the next kind of section of the talk, which is to kind of talk about what is this kind of production Shiny application scaffold that we want to build to stick this into, I do want to very briefly open the floor up for some questions around kind of the concepts that I've been laying down, right? Like if you're a little bit lost with respect to like the MRG solve piece, don't worry about that. You can always go back to the video, but like, this is your chance to ask me a question. So if some of the conceptual ideas that I've been throwing down are something you've experienced or have questions about, like someone else on this call has almost certainly had the same types of questions. So please speak up.
Devin, there's a question, is the global R required always?
So global.r is not required. So there's actually, at this point in time, RStudio does so much intelligence around a Shiny app that like, as soon as you just open up something and start throwing in some Shiny in there, and then save this thing, hello, it's going to be like, oh, hey, this is a Shiny app. You want to run it? You want to deploy it? Like, sure, I got you. So this requirement around having particular names has been dramatically loosened kind of in more recent versions of Shiny. But there are still some conventions around like the sourcing order. If you do use something like global.r, or I think there's like another convention around the www folder for injecting like CSS and HTML. So simple answer, like, no, you don't need global.
And this is a personal question from me. So I think people often dive into Shiny because it's shiny, right? because it's new and it's exciting and it's allows you all of this interactivity. What you've just shown kind of in your kind of preface to turning that into Shiny is actually quite a nice way of working with our Markdown to get, close to what you want to see. So at what point do you make the leap between, okay, I'm just working with an R Markdown, and perhaps you could parameterize that so that you could feed in the input numbers that you're interested in and just get an HTML page back, versus this has to be now, I'm now making the leap into this being a full-blown Shiny app. What helped you make that decision?
Yeah, great question. So the thing that Mike just mentioned is one of the kind of other pieces that our Studio Connect can do, our Studio Pro itself can do, is this idea of adding parameters even to our Markdown. And so you can actually start to define some like params up here. And then I'm going to probably butcher the syntax a little bit, but like you could define a parameter like this, and then I think you can give it some like reference value. Or you might have to define the type. I honestly, like we could pull up the docs real quick, but the idea then is you could reference this in here and say, this is params $this. And then in our Studio Connect, you even can have an interface where like it'll give you those like input fields where you can set those and then like click knit. And so you get kind of like a pseudo dynamic document that can like be generated for the stuff that you just asked about. The boundary from which I start to shift away from our Markdown into Shiny is when you do that way of taking this approach, you have to compute everything. So it works for this app, right? I can sit here and I can say, all right, this app is pretty small. I change a couple things right here and I just run all again. Or I click knit and I'm going to go look at these outputs together. But when you start to get to these non-trivial applications where you might want the user to navigate through a bunch of options, right? Oh, you want to change a couple different parameters all at once. Maybe you don't. Maybe you want to look at that scenario and then try another one. That's when Shiny like kind of surges past our Markdown, and the user experience really starts to trump that needing to kind of wait for everything to be calculated each time. So that's one place. That's kind of the main place. The other thing that kind of is in the same vein is you have to run the R Markdown end to end. So there can be certain archetypes of applications, especially ones that like need to hit databases or otherwise, where you can kind of cheat a lot with respect to like in this setup chunk, you can do a lot of work. In this setup chunk does not necessarily get run for each user that logs into the Shiny app. So one of the nifty things about Shiny is actually like multiple people can get on the same R application thread. And so what that means is that anything that is set up that's run kind of during the instantiation of the application only needs to get run for the first user that logs in. So if you have like, I need to query the database and do some calculations that take, seconds or minutes even to do, only one person has to sit there watching that loading bar. And so between those two scenarios, if you have to do a bunch of preloading, that it would be a pretty poor user experience with respect to needing to knit the R Markdown each time. Or if you start to deal with a degree of complexity that that makes sense to be able to only have to compute or deal with certain parts of an application at a time. That's when I start to reach towards Shiny. But to your comments, I have seen a lot of Shiny apps that shouldn't probably have been Shiny apps. They should have been our Markdown documents, and it should have kind of almost finished here. So like, I do want to convey that like this is actually in many times like an endpoint even of saying like I can hide all these code chunks. I can echo as false, include as false, and just include these outputs with some written up information, And these can be some fantastic reports that people take, especially if they're like, let me explore 3 or 4 scenarios and that's it. You can start to give them some degree of customization around that without, the infinite customization, but also the overhead associated with maintaining a Shiny app. Okay. If there are more questions, post them in the chat. Kind of the next pause, I will, or additional follow-ups to that. I would be absolutely happy to talk all day long about those kind of conceptual boundaries. But we're gonna now kind of dive into that, what I'll call the productionization of a Shiny app, which to me is something that I'm hoping that by giving you this kind of scaffold that you're going to be able to run with. So to kind of preface this as I open it up, there are, talks and other people kind of discussing things like Shiny in production. There are frameworks that give you some structure around how to build Shiny apps, like one of which that's reasonably popular is Golem. So I'm not using those patterns here, but that doesn't mean you cannot use those patterns in this. This is, again, a very simple scaffold that I want to focus not exactly on the specifics of this code itself, more around what this is doing. And so irrespective of whichever kind of like framework or extension or other patterns that you're using, you can still apply these concepts. So what are these mythological concepts that I'm talking about? Well, one of them that I just kind of laid out was that idea of working to define as much as your business logic and your kind of control flow before you even get to Shiny. This next one is that we should be hyper vigilant around the consideration of the fact that the code that will be running in Shiny is going to have no user intervention once it starts actually running on RStudio Connect in a Docker container, wherever you're going to actually deploy it to. And this is an area that causes an enormous amount of grief into that like targeted or markdown space. But when you have these applications that start to live for a long time, you're going to actually start to get into that tail of where much of the work, even to 50+% might just be straight up maintenance, diagnosing, debugging, extending the existing application, not this kind of greenfield code writing. And so we want to position ourselves from day one to have a structure that allows us to be successful, to understand what the application is doing and be able to kind of triage and reconcile when our mental model of what the app should be doing starts to go astray. Yourself around being able to address those in kind of a timely, consistent fashion. So how do we do this? So the kind of 2.5 concepts that I want to show what are in this scaffold is configuration. It is and then it is logging, and then it's kind of either a subset or a superset, depending on the perspective you want to take of it. Is this other thing called tracing? So those are the three of the pieces that we want to discuss, in the scaffold. And you can see that this is like 50 lines of code, but this 50 lines of code is going to give you an enormous amount of kind of flexibility around from day one, being able to see kind of like what your application is doing. And again, the scaffold is in the kind of folder. So I encourage you to take this, extend it, do what you want with it. And so the two things that are kind of framing the scaffold are one, use of the configuration package. I'm not going to speak too much to this because I think this is an RStudio package. They've done a great job of talking about it in like the Shiny in production and some of their other docs around managing Connect. And so, but I do want to show you at least like what we from day one start using this configuration concept for. So the idea behind the configuration package is that it allows you to define in kind of a YAML file some values in a way that you can then also specify like kind of a namespace for this configuration. Which of the values do you care about? And so the kind of three or more that you might always want to have are a set of defaults, what I will call a production environment, and then the RS Connect environment. In particular, one of the pieces of the goodies that that RStudio Connect does by default is it sets the appropriate environment variables to tell the Connect package, the config package, to use this RS Connect kind of namespace. So anything that you put underneath here is something that's going to automatically, if you don't make any other changes yourself to environment variables or otherwise, this is the thing that is going to actually, these are the values that are going to be set. So one great example of the differentiation between like this versus this or this is the use, for example, of shared secrets. So you might have some secrets that you're storing on your laptop. Maybe it's some AWS credentials to reach out to some S3 buckets or to connect to some database with a username or password. Or maybe it's something simpler, right? You need to interact with the database. And so you stand up a local version of the database, like living on a different URL. So you might go in and say, by default, I want the DB, URL to have some path, localhost 4973. Whereas with RStudio Connect, this DB URL might be some production database living in Amazon or wherever you're running it. So this immediately allows you to templatize and control some of these values that that I think if people don't know about things like the config package, they start trying to jam this into code, right? If something, use this value, else use this other value. Like when you find yourself kind of doing that conditional logic, one place that you can reach to is the config package. So we're gonna from day one have this configuration object, which means that we can also then start to make sure that when we get into situations where we might have something that we want to set conditionally, we make sure that the state of that is defined in the configuration, not in the app. For example, and this kind of dovetails into the next package that I'll show you. So this is one of our packages. It's called Logger, but there are a couple other logging packages. Again, you don't have to use the Logger package per se, but the pattern of logging is something that's extremely important. And so if you want to go check this out, it's on our GitHub. And you can kind of go read around the specifics of what Logger does. But the big thing that it does is it imbues kind of two core constructs. One, which is called leveled logging, and then the other one, which is called structured logging. And so the idea behind leveled logging is the idea of you can have different levels at which in certain contexts, you might want a log message to be displayed or not. And so for Logger, you have like a trace, debug, information, warning, or error levels. And so you can decide how you want these messages to be displayed depending on your environment. So for example, by default, the info level and beyond, so like info, warning, error, are actually printed. Otherwise, that message just nothing happens to it. It never does anything. And so if by default you run this, nothing happens. But if you set the level to debug, now when you run it, you can see it. So this gives you flexibility to do things like while doing development, you want to have much more insight into the data flow within your application, but you don't want all of those logs to kind of pollute once you actually deploy this into Connect, because you don't need to see all of that. It would just be too much. And so you can tune in, for example, the configuration package to say, what is the level that you want to show? And so you can say, in production, maybe I want to set to the debug level or maybe the info level. But otherwise, if I am currently just not in production, I might actually want to focus on the trace level. And so the other thing that Logger does is it allows you to specify multiple formats, and you can use these formats kind of combined together. And so in this case, if you kind of read what this is doing a little bit, is it's actually creating two output streams. One is it's printing to the console as regular text, but then the other one is actually JSON formatted logs that print to a text file. And so I've actually run this app once just to boot it up to show you what happens then is you actually get truly structured JSON logs. Why? Well, one of the key things around logging that you have to kind of early on decide for an application is how are you going to consume those logs? If you are going to consume them as a human being scanning through them, it is not worth putting a bunch of extra formatting of JSON on top of it. It's just more stuff your brain has to scan through. Especially compared to like if you look at what the the default text logging does, it actually colors things differently. Like worn is yellow and error is red, so it makes it easily scannable. It's more digestible because it doesn't have all the fields with the quotes and the other kind of baggage of JSON. The problem with this, though, is that if you do it this way, then it makes it much more difficult for a computer or a system to process those logs. So on the counter, if you have some other log aggregation framework, you're doing something to slurp in those logs, then having like JSON structured logs allow you to process them. And in fact, I think somewhere here, yeah, you can actually even see that like here's a pattern from which you could actually pull in that entire log file as a data frame quite easily and then start to actually process it. And so you can kind of go in and say, for example, give me, the logs from yesterday, some user reported an error, and I'm just going to immediately filter for the error type, right? Because you get like the error level. So you could just start to strip out logs. And this is what also makes it nice for like alerting systems, for example, where you can say, I'm going to have a thing monitoring this file. And if we ever get an error or maybe even a warning, we're going to instantly alert someone. And this allows you to transition from reactively responding to users. For example, someone has to call you and be like, something crashed and help. Instead, you can get prospective pings potentially of saying, an application is reporting these errors. You might want to go investigate, and you can kick off investigations or otherwise before the user even has full time to kind of aggregate things together. So you can give a much more cohesive experience. And these are the types of things that cause that like poo-pooing by IT groups, because they say, well, do you have logging like that? Do you have that stuff set up? And then if you kind of scratch your head and like, I've never heard of any of that stuff. And they kind of, shiny, it's not production ready. No, it can be. Like R has, and not just using Metrum's things. There's a bunch of logging packages that give the same thing. This is just ours. They kind of happen to all evolve around 2 years ago. I wrote this one about 2 years ago, and this was just like a straight up shameless kind of a reference, like our implementation of this super popular kind of logging package for the Go language that has that exact same thing. So I was just taking patterns that were, again, like well established in other languages and saying, how do we make this available to R? So if you know where to look, you can actually find a lot of those pieces that are being used kind of in full production systems, and you can start applying them from day one. So we have configuration. We've now set up some logging, and in fact, we have some logic around this logging to change it, whether it's in a production environment or if it's in our development environment. The last two pieces that we kind of have here really encompass two things. One, you want to make your application as easy as possible for the user to be able to tell you about it. And so for one thing that I like to start out with is, without any other pieces of application logic, stick some version in there, manage that version in your configuration. And so that way, like, put this just somewhere in your UI. You know, right here, it's just sitting there. You know, eventually get it in the top right corner or the bottom right corner or somewhere, such that if someone's using your app and they're like, I have a problem, and you're like, well, what version of the app are you using, right? It's in active development, or, you know, are you in a different environment or something? They can immediately tell you, and you can start that diagnostic process without even having to be like, oh man, where is it? What version is it? What were they doing? So empower the user to be able to figure out and convey to you what their kind of problem might be. That's piece one. And then piece two is just a little code snippet here that I want to explain real quick that kind of sets us up for this concept called tracing, which is really just being able to track what is going on during the kind of life cycle of a computation in a way that we can unravel pieces. So what are we doing here? Well, in the server, we're setting what's called a session ID. We're making a copy of our logger, this kind of global version of the logger. So it's specific for this particular session, right? Because multiple people could be using this, and we want each person to have their own copy of the logger. And the reason for that is because we then want to actually set for that single person their user and their session ID. Now, what does that give us? Well, what we can see is actually, because I've run this and launched it, I just launched it, you see that as soon as that user logs in, you know, we have some user, which is unknown because this isn't actually deployed through like an RStudio Connect instance, so that it's not attributed to any user yet. And it has this randomly generated but consistent session ID. The reason that this is important is because as you start to get multiple users concurrently using your application, so I'll open my browser and I'll open another session while we're at it. If we look back here, we actually see that multiple sessions have now been started. And so this allows us to unravel the individual user's actions in these logs, even in the face of multiple users using it at the same time. Otherwise, what you can some people kind of accidentally walk their way into is they're like, I'm going to log, and then they start putting in some log messages, and they're, you know, like, log, you know, an error occurred, da 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 da. And what the problem becomes is if you have multiple users using your application at the same time, you get those logs, but they're all interwoven together. And so you can't actually differentiate or I shouldn't say you can't. It can be a lot harder. You're not guaranteedly able to differentiate what log messages corresponded to which user. And so this way, by attaching the session ID and by pasting in the user, you have the bits of information you need to be able to chase down, stratify, filter, all the way down to that single user using your application in one place. So this is where I would start. And so, oh boy, we have 13 minutes. And so we're going to take this scaffold. I will save this thing and just call this app. I'm going to show you how fast we can move from this scaffold to that kind of running app. So we have the UI and the server. This is where we're going to be operating against. The first thing that I'm going to do is I'm going to take all of that logic, all of this logic here, and I'm getting this into the server. So what we're going to do here, I'm just going to yank it right into the app, right into this server. Boom. Each one of these code chunks fits very nicely because each one was kind of an individual unit of computation. Each one of these can fit really well into this thing called a reactive. So this reactive is a piece of code that ultimately is going to be dependent on some input and we're going to wire these inputs up in a second. But so now iData comparator is actually a dynamic value that will change over time. Same thing, summary calcs. We're going to grab this. This too is a reactive. Now we have to be a little bit careful to make sure that stuff is kind of coming out okay, and that we're kind of doing what we need it to. In this case, for example, I was copying and pasting a little too fast. I care about the out comparator. This thing is part of just this. So I need to kind of reorganize this a little bit. So this reactive is this piece. Output comparator is what we care about. And I know this because this is also something that is going to be used in like the summary calculations, and then ultimately is also going to be used in that plot. So we can let's keep moving this business logic over. So we moved those two. That's pretty much it, right? And I might do something like just even comment that out just to be like, yeah, I've gotten that over into the app. Then I am going to grab these outputs. So we have one table, one plot. So we'll come in, we're going to grab this summary calcs. This is going to be an output $table summary. And it's going to be some sort of like render table, render data table. And it's going to be summary calcs. Now with Shiny, the only difference we have to change now is that things that are reactive need to actually be invoked kind of like a function. So if you don't invoke it, it's going to give this kind of funky like reactive context error. So we do need to actually do like the one piece of as I move this stuff over is you do have to kind of chase a little bit and find where are the pieces that are reactive. So in this case, my summary calcs is reactive, my out comparator is reactive. And this is where we can even leverage RStudio a little bit to help us out. For example, when I select out comparator, it's even highlighting and being like, hey, I have this down here for you. So you go, okay, thank you, reactive. So I've got these guys, I've got this one, comment, need to grab the ggplot code as well. Output $p summary hist under plot, paste. Same thing, I'm going in here and I'm like, what things, oh, there's one, boom. Summary calcs 2 is another one. Boom. So we've got our reactives, we've got our renders. We still need this output reference. This is the kind of last piece of this meat before we get to these kind of constants. So we're going to go in here and we're going to chase this down. And so where we had it was we had this and the other constants kind of defined up here. So I'm going to just grab all of this stuff, right? Because this was my kind of up front, up top setup stuff. So this can even go up here, and I'm being a little bit messy for the sake of time, right? Normally I'd have this stuff reconciled a little bit more. I know I have some duplicate packages loading, but this stuff is going to be processed and only needs to get processed once. So this is all the server stuff that I think we need. So the last piece is just our 3 inputs. And then we should be able to run this. So each of these are numeric. So we're going to come into our UI and we're going to say, all right, we just have numeric inputs. And we have this input ID, CV for IKIU. And then you have to give it a value. I think this was 0.09. And then you can do some bounding if you so choose, and a step size. So we'll say the bound of 0.0, or we'll do min 0, max is, I don't know, just 1. And our step size is 0.05, 0.02. So let's make a couple more of these real quick. Scaling factor, right? The value is going to start at 1. We might go 0 to 3 in increments of 0.1. And then the last one is our threshold. Badness. Starts with 200. Min of 100, max of 1,000, steps of 50. All right. So the last final piece, final 2 pieces, is we need to pass these into the server and actually leverage those values. And we need to also get these plots actually showing up. So let's do these plots real quick first. So we're going to table output that, and then we're going to plot output this. Where's my UI? That. So I've now got my tables and plots. So the last thing, we've got these things. So again, I can scan here. The only change that we really have to make is just putting that input $. So the scaling factor, same thing. Input $. And that threshold is, okay. So nothing ever runs the first time, but we're going to give it a whirl anyway. Maybe it will actually run the first time. We fire away. Boots up. We've got our inputs and we've got our outputs. So as I change this, so let's just say I change this to 0.2. It's going to recalculate. And now we're going to see now that if that had changed, our comparator now has none over that 200 threshold. And you could keep running for that. You could also see, what happens if this was 20% higher? And now you can see these things completely shift, right? If this moves up to 20% higher, it absolutely completely changes the, that this would actually cause way too high of concentrations, a huge amount of time, almost, well, 100% of the time, it's too high. So this in and of itself is a huge deal. You shift it down and you see how things collapse. I also said that I would, show you what happens in to kind of deploy this to production. So I got 3 minutes left, so I'm going to show you in less than 3 minutes, and then open it up to questions as people can kind of meander off for the rest of their day. So publishing on Connect is really straightforward. In Metworks, we have on all of these kind of what we call workflows, we also have an RStudio Connect instance running. And the Connect instance on Metworks is kind of reasonably set up like a vanilla Connect instance. So what I'm just going to show you here is no different than if your company has another Connect server. So what you can do is you can just click publish. You can choose the stuff that you actually want to publish up. So we can take out a lot of this stuff. That. And you can kind of click your way through what you want to actually push up there. I'm showing you this because one of the things that when we actually publish this publication pattern of clicking publish like this is the last piece that I want to say is absolutely something that you should get off as fast as you can. It is nice as a user, but even as you saw here, having to check or uncheck the data and the documents and the pieces that need to go up there is absolutely like bugs or disasters waiting to happen. So while this is publishing, and actually it's already done publishing to Connect, so we can actually see this thing is now running in Connect. So here it is now running in Connect. But the piece that I wanted to show you was that when it publishes, what you can actually look for is in this deploy at the very top, it'll tell you what it's doing under the hood, which is actually just running the RS Connect package. And so I encourage you all to, steal this, learn from this, understand this, and then start to actually write this so that you actually have kind of control over your own destiny of the specifics of how it's going to deploy in a reproducible fashion. In particular, you can do things like define the app files. You can define this once, and then that you can go run this deploy app over and over and over again, and it's going to work successfully. This is also positions you to start to do this like programmatically. So if you take this app and were to say push it into a version control system, and then the version control system needed to deploy this app to various places as a kind of a quality gate, you can have the version control system itself call this like deploy.r script. And that way, again, there's no human intervention. And so you get that auditability and that reproducibility around how did an application deploy. So I know that that kind of end bit was kind of a race to the finish. But I do want to now kind of open up the floor to kind of questions, comments. It looks like people are starting to drop off. And so, but I'm happy to stick around if we don't get kicked out of the meeting. We might have to give this meeting to the other session.
Actually, I don't think we will, Devin.
Okay.
So we can answer questions for as long as needed. What questions do people have? Sorry, Devin, just to kind of housekeeping thing, to reiterate, you said at the beginning of the session there that a lot of the stuff that you've demoed there, you were working on quite late. For example, I can't see scaffold.r in the materials and the content there. Can you just remind people where to find that?
What we'll do is R Pharma Shiny 2020. Make this thing public. I'm going to push this up plus all the live code so that you all have access to this shortly. I wanted to kind of keep this separate from Kyle's material because like The package sets and otherwise were a bit different. For all of our Metrum packages, we use a tool called Packager to install all the packages kind of in parallel and reproducibly. So if you want to pull this down and bootstrap it, if you want to use regular install.packages, like here are the packages you need. If you want to use our Packager tool, it is open source and likewise available here. This works on kind of Windows, Mac, and Linux. You just go to the releases.
I can recommend it.
Changing, so I can't find it. I can never find it anymore. I think it's here. Yeah, here we go. So you can go grab these releases for Windows or Mac, drop this on, and run Packager install.
Great.
So either
and
one.
Also, I guess because you live coded that, it's worth people going back and revisiting the video when it gets published so that you can see and follow along once you've got that material as well. Thanks.
Yes.
Are there other questions from folks? I didn't see many other comments or questions in the chat.
Nicely done, Devin.
Yep.
Good. So, the statement.
I've never seen anyone deploy an app in an hour and have it work, ever.
Lightning strikes every once in a while. So the a core takeaway though is, you saw me just like flashing around. I do this a lot, so I'm comfortable with it. But I think the first app I kind of deployed myself, it took me like a week to kind of flounder around through it. So don't get disheartened if you try to jump in and then all of a sudden you're on your own. You're like, whoa, what is all this stuff? It's okay. Increment your way through. Don't feel like you have to kind of know everything immediately. But from an exposure perspective, I hope this kind of brings up some of the places you can strive to eventually get towards, right? You don't need all of this stuff from day one, but know that it's there. Know that it's going to give you more robustness. It gives you a vocabulary to think about, right? One thing we really didn't get to, but this is where what you can start to do here is where you start putting log messages in here, where you might say, I'm going to actually drop in some of the data fields of what is the value of IKIU equals, this. And what this can give you to simulate with value. What this will give you, and what we'll see is when this thing kicks off, is if we open this thing up, you can see that it's going to start to drop in. This was the IKIU value it was using in the simulation. In addition, now my stuff's all over the place. As we change this, right, 0.04, and we change the scaling factor, what's going to happen is each of these things is going to get logged. These logs allow you to do things like go back to your R Markdown document and diagnose what the heck was the user doing. Why did it give them an error? Was it something we weren't expecting or were expecting? And so being able to attach data around what the user is doing actually gives you the ability to reproduce a lot of these things outside the scope of the app for diagnostic purposes or auditability, traceability purposes, et cetera, et cetera. So you can start to really build off of these concepts to give you a lot of the things that not only do kind of production applications care about, but pharma and specifically cares about with respect to traceability and otherwise. So yeah, we'll keep this MetWorks instance running, probably for the duration of the conference. So feel free to revisit it. For those of you that tuned in a little bit late, remember that you can go to the sign in, sign up, sign something. The sign up page, throw in your email. It actually doesn't even need to be an email. It can just be anything. And it's going to provision you a user and give you a password that you can log in. As long as you use that same set of credentials, it'll always give you back the same password. So that if you log in, forget what your password is, go back, plug in your whatever unique identifier you so choose, and you can get back in to play around some more. So I'll be around for the conference. I'll be talking about kind of package management in the enterprise, and specifically focusing on internally developed packages and how you can support and enhance your internal developers' capabilities. So, whether it be Shiny application development, packages, or anything else to do with the R or other language ecosystems, I am always happy to chat about it, and don't hesitate to reach out. The last thing to kind of close with is, I think my contact information is floating around from the workshop, but just in case not, I'll flash this up on the screen. It is Devin P at Metrum rg.com. So reach out to me for any questions. Happy to chat. Enjoy the rest of your Friday afternoon, or for people like Mike, their evening. And thank you all for sticking around.
All right.
Thanks so much, Devin.
Metrum team, fantastic. I've got some really good feedback and emails already pouring in. You did a great job. So thanks a lot.
Great.
Yeah. Righty.
All right.
See you, everyone.
Thanks, everyone.